Hi there. MKE, can you hear me? I was actually planning to hold this session on the Irvine Discord, the Irvine 2B Discord, because I think that's where most of the people are. It doesn't make a huge difference to me, but I think it makes more sense to do it there. Do you have the link to the 2B Discord?
Glitching on my laptop. What did you say again?
Hi. I was just saying that since it seems like most of the Irvine students are on the 2B Discord, we were probably going to, if you want to talk and discuss live, that will be, I'll be participating in the 2B Discord room and streaming that to YouTube for people who want to watch, rather than this particular voice channel that we're currently in. Does that make sense?
So which one do I go on?
Yeah, so if you go to the Irvine Students channel, you can see that Cosmic Snowman shared a Discord link to Math2B.
Yeah.
See it?
Uh-huh.
Okay, well, I'll see you there in a second.
Okay. Thank you.
Sure. Confirm. Okie dokie. Hello. Why am I getting feedback? Why am I getting feedback? 1, 2, 3. 1, 2, 3. Testing. Okay. The echo is gone. Okay. Hi, people. Can you hear me? Is my audio okay?
Yeah, it's good.
Good, thank you. So the way that this works is when there's a couple of people who want to volunteer and talk, we can basically, I share my screen. You can see I'm also the other person, everything done wrong. I share my screen with OneNote, and you can see what I'm writing instantaneously. But for people who are maybe a little bit more shy, I also put a recording up on YouTube. So that's how this sort of review session works. How are you all feeling about the class?
I would like to not fail it a second time.
I understand. Did you drop it the first time, or did you take it all the way through?
I took it all the way through because I got a D+, so I could take the classes that had this as a prerequisite still.
I see. Does it work if you get a better grade? Does it replace it? Is that how?
Yeah, that's why I'm retaking it.
Gotcha.
Yeah, I'm not doing so hot in this course.
Can I ask?
I took. Yeah.
Sure. Go ahead.
What happened?
Go ahead. I'll ask after.
I took BC in high school, but then it's like I got a 3 in the AP exam, so now I have to take it in college, right? But it's so hard compared to what high school is.
Yeah, it definitely is a step above. I myself took BC calculus as well and placed out, so I went right to multivariable. And I think I kind of skipped that intro weed out phase. You know what I mean?
Yeah.
Man, I didn't even score well enough on AV to test out of AV.
Oh, what was your question gonna be? Or were you gonna ask?
I was going to ask. What was I going to ask? It's sort of the same general question. I guess I'm trying to figure out where the difficulty in this material is, because most of this stuff I've known by heart since high school, right? I can still more or less remember what it's like to struggle with it, but how do I put it? Like, integration by parts is something that is super fundamental and is something that I used, for years afterwards. And the fact that they're teaching it in, what appears to be 2 weeks, right? Someone told me the syllabus, there was only like 2 weeks between midterms this time. Is that right?
Yeah.
That's kind of crazy. That's I think that might be a little bit less than ideal, to be honest. But we're going to give just a minute or two here. I have some other people indicated that they were interested and wanted to join us. So I'm just going to make sure that they know where we are. Let's see. That's NKE. Gotcha. So today's general format is going to be, I would say, about 50-50, maybe 40-60, a review of the concepts, and then just a ton of practice problems until we can see, a couple examples from each type. And the hope is that this is going to be more or less a compact review that should give you almost everything you need to know to do well on a midterm. What I do want to ask, though, is, at this point, how do you all feel about integration by parts? I would say that's, the biggest takeaway from this class. But at this point, do you think you understand what integration by parts is? Do you have good intuition for it? What are your thoughts?
I'm usually okay with integration by parts. I think that's one of the actual few parts in this midterm chunk that I actually know how to do with like more than 50% accuracy.
More than 50%? Okay, gotcha. Do you feel like you could if you were just given a blackboard, can you explain why integration by parts works?
Why it works? No, I can do it, but not why it works.
Okay, so I think it wouldn't be a bad idea to maybe start with that. Okay, I guess we're gonna get started. As we go along, just a quick introduction to myself. I'm a math hobbyist. I graduated in math CS. I like to help people out when I see them struggling. I do this for free because I want to make a large impact. I have some other students from York University in Canada, and I think UCSD, where, when I try to help one person, I try to record it and broadcast it so that it can help 50 or, even more people. But the general idea here is, if you do know other people in the class who are struggling, who might be interested in this, please reach out to them and let them know about this, because when one explanation can work for one person, it can usually help a heck of a lot more. Right? So with that, we're going to get started with our first discussion, integration by parts. Someone sent me the syllabus the other day of what you covered in chapter 7. So I'm basically going to just go along there. And for anyone who wants to have questions, please stop me. This is part lecture format, part discussion format. And the couple of you in the Discord voice channel right here, I want you to stop and ask questions when things don't make sense, because I don't remember what students organically would ask at this point, right? I've known this stuff for years. Make sense? Ready to get started?
Yep. Sounds good.
Okay. So very first thing is integration by parts. I'm assuming that this is probably the most tractable part of this unit, but I think it's still really good to get a good foundation, because when you are in the thick of trig substitution and just seeing a problem and need to identify what it is, I would say that the first thing you try is probably see if it's an easy U substitution, and then see if it's integration by parts, and then try all the more difficult stuff afterwards. By the way, can you all see my screen? Is there a bad delay or anything like that?
I think it's fine.
Okay.
Yeah, we can see your screen.
Sounds good. So what I'm telling you is integration by parts is just the product rule in reverse. I'm sure your professor explained this, but this actually went over my head when I first learned it, and I was basically just doing the UDV pairs for months without actually understanding why it worked. Does this concept make sense, that it's just the product rule in reverse? Have you heard this before?
Yeah.
Okay.
I've heard that it's the chain rule in reverse.
I would say it's specifically the product rule in reverse. U substitution is kind of the chain rule in reverse,
Oh.
right? So what happens is, okay, you have fg prime, right? Well, okay, that's f prime g plus fg prime, right? And what happens is that we just take the integral of both sides, right? The sum is linear, so you can apply the integrals independently. Yeah. So the integral of the derivative is just the exact same thing, right? So you can imagine like writing a little dx next to each one for the notation's sake. But this is just going to split back fg, and this is going to be f prime g dx, and this is going to be fg prime dx. And the idea here is we just move this, I think, right along to the other side. Sorry, this one. We're moving this one right along to the other side. It's f and g are symmetric here, so it doesn't really matter, but I'm trying to keep things sort of lockstep with notation. So at this point, it's f minus the integral of f prime g dx is equal to the integral of fg prime dx. And the idea here is most people at this point just use a notation u for f and v for g. Yeah? And at this point, this becomes just a statement uv minus, well, g is sort of v, and f prime dx is basically du. This is the justification for why integration by parts works. The idea is basically, if you find some u and dv splitting, right, maybe it's a lot easier to solve for v du instead, because uv doesn't have any integrals at all, and this term is really nice. But basically the idea is to say, okay, maybe u and dv is not so great, but maybe v du is a heck of a lot easier to think about. That's fundamentally what integration by parts is. It sort of shifts the complexity, in a very broad sense. And the idea is that you always want to power things down until you can get something very easy, something that you already know how to do. Yeah, right. So I saw the channel 7.1, 2, 3, 4, 5, 8, and then 11. So we're not going to cover 11 today because sequences is a lot, and I think we have enough. But we're going to cover the rest. Don't you worry. Okay, so with integration by parts, I think I know that you probably all don't have too many questions on it compared to the trig stuff, which we'll get to soon, but I do want to cover some of the big pitfalls I see with integration by parts. Yeah? Okay, so an integral like this, e to the 6x dx, would you all feel reasonably comfortable at this point if I just asked you to integrate an indefinite integral like this? How would you choose your u and dv pair?
Taught us lie it, I think. I don't know how to say it exactly.
I'm sorry?
They taught us like a rule. It's like lay it, I think.
Well, I thought it was lip it, right? It was like
Interesting.
natural log, inverse,
Yeah.
powers
It's
of x.
L-I-A-T-E.
Interesting.
really?
I've never heard this
I thought it
analogy
was
before.
L-I-P-E-T.
Laite.
Okay, so bottom line, how would you do the splitting in this problem?
X.
X is you.
Okay,
Yeah, x is u.
and this is?
dv.
dv, naturally, right? And the reason that this works so nicely is because, well, okay, so if u is equal to x and du is, so I know I'm just singing to the choir right now, but I think it's important for comparison to a more complex case in a moment. But if dv is equal to e to the 6x dx, right, then this becomes, v is just the integral of that, so it becomes, I'll do it in my head, it's just 1/6 e to the 6x, right? E is quite nice. It just pops out the constant. And then at this point, it just becomes uv minus v du. So this becomes 1/6 x e to the 6x minus 1/6 integral of e to the 6x on its own. And you should all know how to do this, right? This just turns into 1/36 e to the 6x. So that's really cute and pretty, right? That's. Do you see what I mean by it sort of shifts the complexity away? this x was making things kind of nasty. There wasn't a good u substitution here. So essentially what this u du dv v thing did is it powers the u sort of down, right? It takes, instead of thinking about x, you get to think of the derivative of x. So it essentially says, well, the complexity was because it was x to the first power. Now it's x to the 0 power, which is a lot easier to think about, right? But the nice thing about this other term was that e to the 6x, its derivative is itself. So it didn't really get more complicated, right? This was sort of like almost getting like a free lunch here, where one of our things got easier, u got simplified, but then e, because we chose it in a very nice way, it didn't really get more complicated because e is just that nice. Does this intuition make sense? We're always trying to find the nice pairings where something gets simpler.
Yeah, that makes sense.
It does.
Okay, so then I won't necessarily do all of it out, but a problem like x squared e to the 6x, how would you do this? Talk me through it. We don't necessarily have to go through all the parts because it's tedious, but someone talk me through the big idea here. What would you do if you were confronted with x squared e to the 6x?
I would do u as x squared,
Okay, u as x squared.
and then dv as e to the 6x.
Okay, and again, I won't do everything out, but this is going to roughly turn into e to the x squared, du is equal to 2x dx, dv is equal to e to the 6x dx, and v is just equal to 1/6 e to the 6x dx. Okay, so what now? Did we make progress, or was this a dead end? Did we make progress?
Progress, because then you can do it again.
Yes, exactly. So if you just write out the uv minus v du, this is beautiful, actually. So what is this? 2/6 is a third, right? This becomes x e to the 6x dx, right? Because look at how we bumped down the complexity. Initially, it was x squared e to the 6x. Now it's just x e to the 6x, right? We bumped the complexity down on the u, and because e is really nice, we raised it. We raised it up by an integral, but because e is nice, it actually didn't get any more complicated. So we kind of like cheated these polynomials, where we cheated these functions, so to speak, right? We made it into something simpler, and then you would just have to do the integral again, and then you would be, you know how to do this because that's just the exact previous problem, right? So one thing that I do want to bring up, though, is a very common mistake that I see from students doing integration by parts. It's something that I occasionally make myself. But when doing a definite integral, right, let's say that you were doing -1 to x e to the 6x, right? Okay, let's integrate it the same way and do u is equal to x du is equal to dx, v is equal to e to the 6x dx, and dv is equal to, well, I guess this is the integral of e to the 6x dx from -1 to -2. So, you as a student, you might think that, okay, then this is just 1/6 e to the 6x from, -1 to +2. And you might just evaluate this to be, what is this? 1/6 e to the 12 minus e to the -6. Is that right? Yeah, I think those calculations are right. So is this allowed? Is this right?
No, right? Because wait. Actually, I have no idea.
No, it's really good. This is something that actually tripped me up after I hadn't seen it for a little while and had lost some of my intuition. But this is actually really, really bad. The idea behind definite integrals is you can plug in the -1 and 2 at the very, very end. Yeah, you can plug it in once you get to this point of x squared e to the 6x. But during this u dv stuff, you need to think of, I'm sorry, this should have been dv and v, my bad. You need to leave v as a function of x. You can't just evaluate it. The reason this whole thing works is because, the whole explanation about the product rule and chain rule stuff was talking about f and g, or u and v, as functions. you can't just arbitrarily plug something in halfway through and turn it into a straight number. This is actually really similar to the calculus 1 mistake, where let me know if you've ever made this mistake in calculus 1 before, where you have some function and it's like f of 5 is equal to, like, say 10, right? And you're trying to find the derivative at f of 5. And one thing that first-time students are really tempted to do is just take this expression and take the derivative, right? Then this, because this looks like a constant, it becomes 0. But the reason that this is wrong is because you can't just take the derivative of, like, some straight number. You need to take the derivative of a function before you plug in the number. You can't plug it in and then take the derivative. Does that make sense? Do you recall yourself ever making this mistake before?
Many
That makes sense
times.
to me.
Many times. Exactly, right? I feel like almost everyone does this at one point. Like, they see a clever shortcut and they're like, hey, this is so much easier than, messing around with x's, right? Let's plug it in first. Well, this is exactly the same idea, but with derivatives instead of integrals. You can't just evaluate it. You can't just decide to evaluate it at this early stage. You have to keep it as a function essentially until the end, right? And I think this is probably one of the biggest mistakes with the theory of integration by parts, right? I just wanted to really point that out because, I think there's a good chance that at least someone will make a mistake like this when they try to take a integral on an exam and, are under pressure and, they see an integral here, they see the numbers over here. It's really tempting to just write this out. Yeah. But don't do that. Please don't do that. Okay. So now for a couple of practice questions with integration by parts. No, I'm sorry. There's one more big concept, one more type of big pattern with integration by parts I want to talk about. X squared. No, sorry. This is more or less the same thing. If you have something like x squared sine of 10x dx, so we used a lot of exponential functions as our dv. And I'm just making the point that sine and cosine are kind of similar to the exponential function, whereas the exponential function goes to itself in one derivative. Sine and cosine are kind of like complements, where sine goes to cosine, and then cosine goes back to, well, minus sine, but the minus isn't a big deal, right? But the idea here is that sine and cosine, I would say, you know how I said, and in very rough intuitive terms, I like to talk about complexity decreasing or increasing. E is such a function where either its derivative or its integral just goes back to itself, so it neither increases or decreases. Sine and cosine are pretty similar. They don't jump back to themselves in one step, but they do jump back to themselves in about 2 steps, right? So that's just a piece of intuition that it's really, really nice to consider making sine or your e functions or your cosine functions to be your dv, right? And then if we did u is equal to x squared and dv is equal to sine 10x dx, you can kind of see it's very similar to that that other problem we did, x squared e to the 6x, where after 2 applications of integrations by parts, you're going to solve things wonderfully. Does that make sense? Now, I'm sure that you've all seen this stuff before. I just think that for the sake of a review session, it's really good to just say this out loud. You know what I mean?
Yeah.
Okay. So we're going to do some slightly trickier integration by parts concepts, right? So one of them is x root x plus 1 dx. And the idea behind this problem is that there's more than one way that you could do this. Using calculus 1, you could do this with u substitution, right? You could use u is equal to x plus 1, and then this becomes x is equal to u minus 1. So this becomes u minus 1, u to the 1/2 du. And u sub is honestly pretty easy, right? You don't need to see the steps, right? I'm trying to make a point here, but are you feeling reasonably comfortable if I just skip the steps at this point for this particular problem?
Yeah.
Because this gives you 2/3 x to the x plus 1, 3/2 minus 2/3 2/5 x plus 1 to the 5/2. And for indefinite integrals, always add a c onto the end. Sometimes a little bit sloppy. But the point that I'm trying to make here for this particular problem is that you could have done this with integration by parts as well. Yeah, you could have done this as, oh, I'm sorry. This was actually the answer for integration by parts. And this would have been the answer for U substitution. My bad, I just copied it down from my notes wrong. So this is the U sub answer, and this is the integration by parts. Right? And you can kind of see how you do it integration by parts, right? This x can go powered down, whereas this root x plus 1 can get powered up. But the idea that I'm trying to get at here is 2/5 x to the x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2 plus c. So this is the answer you get from U substitution, and this is the answer you get from integration by parts. And the issue here is that they look a little bit different, right? This one looks like x plus 1 to the 5/2 and x plus 1 to the 3/2. Right? They just don't quite look the same. Does this make you feel uncomfortable? We have two perfectly valid techniques, and we're getting sort of two different answers. Is one of them wrong? What do you think?
So they're not the same answer. They're different.
That's what I'm asking you. They at least appear to be different, right? X plus 1 to the 5/2. X plus 1 to the, what is this, 3/2? Whereas this one looks a little different.
Same, right?
Hmm?
I think they're the same, right? Because if you like this, if you like multiply the x,
Yeah.
like into the, yeah.
They do turn out to be the same in this particular case. If you subtract one from the other, it turns out that they perfectly cancel out and give you 0. But you might imagine that for a slightly different case, they could also differ by a constant instead of 0. Right? I'm just making you pay attention to the fact that the plus c exists. And what I don't want you to do is, if you finish a test early and have extra time and you solve it one way, and then you decide to check your answer and solve it another way, I don't want you to panic if U sub and integration by parts gives you slightly different looking answers. Because with integration, you get some messy expressions that a lot of the time turn out to be just the same or only differ by a constant. Have you heard that phrase, answers differing by a constant? Most people don't care very much when an answer differs by a constant, because that's basically saying the extra c term can just absorb that constant. Is this sounding familiar, or does this sound uncomfortable?
I think it sounds familiar.
I'm sorry? Sounds reasonable?
I think it sounds familiar.
Okay, good. So this comes into play actually a little bit. When later on, when you do your substitutions with trig substitutions, sometimes you choose, sometimes you'll have an expression like 1 minus x squared, and you can either choose x to be cosine or sine. If you do it with cosine, you might get a slightly different looking answer than you get with sine. And this actually baffled me quite a bit the first time I came back to this after a long time. And the answer is that these answers will end up just differing by a constant c. And this constant c is not very important. Either one will be considered correct as long as you didn't make any computational mistakes. But the idea is, in the past, you might have liked to do sanity checking by computing your answers in two different ways to make sure they match up. In integration by parts and integrals in general, that's sometimes a very, very tricky thing, right? I would personally recommend against double checking your answer this way, because I think it takes too much time. Because it's really hard to see whether or not they actually do match up. If you were to want to do a sanity check, I would say instead of calculating the integral a different way, I would say take the derivative instead and make sure that you end up with the original expression. Does that make sense?
Yeah, that makes sense.
Okay, yeah. And even then, that's only a luxury that you get when you have plenty of time. If you are short of time on a test, I would say you really just gotta, trust that your calculations are right and be very, very careful, and then move on when you get the problem finished. Okay, I'm rambling on, but I definitely have more points to make about integration by parts. First of all, are you all feeling relatively comfortable so far? I would expect that this is probably the easiest material of this unit. So please do speak up now if I can explain anything more thoroughly, or if I'm going too slow, or if I'm going too fast, please let me know now while I review my notes. How are you all feeling?
I feel pretty good about integration by parts.
Okay.
I
I'm
think
going
the substitution is very confusing.
We'll get to them very soon, but I do want to point out about two harder problems with integration by parts that I think are very thematic. So one thing you might have noticed is I talked a lot about trying to pare down the complexity of something like x squared or x, right? And you might try to extrapolate this and say, okay, why don't we always choose our u to be the polynomial part? And I would not go that far, because you could potentially get problems like this. How would you do a problem like this with integration by parts? How would you split this up? This one's a little bit tougher, and I think something like this might be a reasonable question you might see on an exam. What would you do about this? Any ideas? Some brave soul. I want a suggestion. How would you choose u dv?
I would make u the square root of x to the third plus 1.
U is the square root of x to the third plus 1?
Mm-hmm.
Okay. Interesting. And then dv is going to be the rest, so is equal to x to the fifth dx.
Mm-hmm.
We can give this a shot.
I would have made u x to the fifth, and then you have to do it like a few times to get down.
U
So
is
like
equal to
math.
x to the fifth.
Yeah.
So both of these are reasonable suggestions, but I don't know how to make these ones work. So I'll write that. So u is equal to x to the fifth, and dv is equal to square root of x cubed plus 1 dx. So I'll start with this one first because I see it. I see the issue more easily. Okay, u is really nice and simple. It's x to the fifth, right? Hopefully every time it just keeps getting bumped down. But dv is so bad. I don't know how to handle the square root of x cubed plus 1 because I need to straight up integrate this to get v, right? And this looks like basically nothing I've ever seen before that I know how to do. I would be very surprised if we could do this integral purely with techniques that we've seen in this class. Cubes are scary. As for this one, well, the issue is that maybe you could take the derivative of this. It might be a little bit nasty, but you could do it, right? But the issue here is that this isn't getting simpler. You know, this turns into x to the 1/6, x to the 6th. Yeah? And what does du turn into? It turns into like 1/2 x to the third plus 1 to the negative 1/2. And then there's another factor of 3x squared because of the chain rule, right? This stuff is nasty. Now when you put it together, this is going to turn into x to the 8 over the square root of x cubed plus 1. You see how much nastier that got?
Mm-hmm.
Right. So with integration by parts, it's almost as much of an art as it is, more so than it is a science, where you have to choose the right breakdown or a really motivated breakdown. And that's why I made sure not to skip integration by parts, because it's the biggest, I would say it's the biggest takeaway out of mid-semester calculus. And I think there's a likely chance that you'll see something a little bit tougher comparable to this on an exam. So here's how I would choose my u and x. But before I choose them, sorry, my u and dv, but before I choose them, I would split it up first. I would say x cubed, x squared, x cubed plus 1 dx. Exactly the same thing, right? No, I hope nobody objects to this. This is just x to the fifth, split up into two parts, right? So if I write it this way, can someone see how to choose our u-dv pair? U is equal to x cubed dv. Okay, I see someone in YouTube chat. Exactly. Perfect. They're suggesting u is equal to x cubed and dv is equal to x squared square root of x cubed plus 1. Now this u looks nice, right? That's just x cubed. dv looks really nasty for a second, but hopefully just for a second. My claim to you is that dv is actually quite nice. Do you see why?
Oh, do you just do integration by parts again on that one?
I would say even easier. What do you use even before integration by parts?
Oh, U sub?
Exactly, right? This breakdown is perfect, right? This breakdown is perfect. X cubed in the inside, x squared in the outside. So yes, this would be an excellent candidate for U substitution. We're already using the variable u, so let's not get ourselves mixed up. Let's call it z substitution instead. So if you chose z is equal to x cubed plus 1, dz is equal to 3x squared. This turns, then v is the integral of 1/3 dz square root of z. And you all should be able to know how to do this, right? You see how tricky integration by parts can be? How do we feel about this problem? Do the folks with me on voice chat understand it?
How did you know how to split up, or like, what order to split up the x5 into?
That's a really great question. So ultimately, this is why I say it's an art more than anything else. This is something that you have to recognize patterns. This is something that you just have to get good at. But I would say, in retrospect, the motivation was that there was an x cubed in here, x cubed plus 1, that was really, really nasty. And if you can think to yourself, I really wish that I could use U substitution. What do I need to be able to use U substitution with this? And so if there's an x cubed in here, that means there needs to be an x squared outside, right? There needs to be an x squared outside. And there's an x to the 5th outside, and there's no reason why I can't split that up into 3 and 2. And at that point, you just have to do a sanity check. Is this part nice? Yes, because of U substitution. Is what's left over nice? Yes, because that's just a x cubed, and that can be powered down as time goes on. So the idea here, and I realize that the word nice is very informal and imprecise, but like it really is just the idea here that we need to choose smart pairs of u and dv's. It's not always obvious. I would assume, I don't know exactly how your professor structures your test. Are they 50-minute exams? Are they 2 hours, 3 hours?
50-minute multiple choice.
Oh my.
Yeah, that's for the midterms are like multiple choice, 50 minutes. And the last one's only like 13 questions.
Gotcha. Well, if that's the case, you might get a situation where, okay, so if they don't even have any open response, then you probably won't see anything too hard. That's so scary. That test is so short. I feel like at that point, it's just a time crunch, huh?
It's scary because
Indeed.
there's no like partial credit for anything, which
I
is
see.
totally different than any of our quizzes.
It's also a time crunch. I remember this midterm from when I took this class last time.
Mm-hmm.
It was so rushed.
I'm sorry to hear that. I'm really sorry to hear that. Yeah, this is 50-minute exams. So long exams sound scary, but as you go on in college, I started preferring them more and more and more. Right? Like open responses are so much better than when everything is partial credit, especially if it gets difficult. But okay. I did want to say one more thing about two more things about integration by parts, and then I promise you we'll move on to like the main course, which is trig subs. Do you know how to integrate ln of x? Do you know how to integrate ln of x?
It's 1 over... Wait, is it 1 over x?
That's the derivative of ln of x.
Oh, that's true.
Right. So d dx of ln of x is equal to 1 over x. This is something that seems a little bit scary at first, but can be done really well with integration by parts. Do you see how?
I feel like it was by making putting like a 1 there or something
Yeah.
like that.
Yeah. I would say that this is a kind of odd situation that still works really well, where u is ln of x and dv is just dx, right? dv doesn't have to be a bunch of complicated expressions. It could be really simple. But this is a situation where we don't exactly know what comes above ln of x, because that's the question we're trying to find in the first place, right? We're trying to figure out the integral of ln of x. But this is basically saying we can relate the integral of ln of x to the derivative, right? We can essentially, what integration by parts is doing is it kind of shifts the complexity from u to the v. So du becomes just 1 over x dx, and then dv is equal to dx, v is equal to x. And at this point, things should be very easy, right? uv just becomes ln of x times x, and then minus v du is 1 over x times x. That's the simplest integral in the world, right? That's just the integral of a constant. And that's the idea. The point that I want to make here is when you practice integration by parts problems and perhaps see them on exam, you really, really want to make sure that you stay kind of light on your toes and look for, try the most obvious possible thing first, but you really got to look around a little bit because there is no set rules for choosing integration by parts. You just kind of have to recognize patterns, right? And I'm trying to give you those patterns as we go along. Sorry, what is this? Do you know how to integrate e to the theta cosine theta? Sorry, there are some big patterns here that I don't feel right unless I make sure to go over them with you. How would you integrate e to the theta cosine theta?
U would be e to the theta. And
Sure.
then dv would be cosine.
Okay, so then u is equal to e to the theta, dv is equal to cos theta, d theta, e to the theta, d theta, v is equal to, I guess this is just my sine theta. So then uv, it becomes e to the theta sine theta minus e to the theta sine theta d theta, right? Okay, well, so this thing is equal to this. Well, okay, we had e to the theta cos theta d theta, and now we have e to the theta sine theta d theta. And if you were listening to what I said earlier, where the complexity of cosine and sine are about the same, you might be a little bit scared and feel like this might lead to a dead end, right? Because it feels like we didn't make any progress in the first step. But what do you think we should do now? Should we try integration by parts again?
Yes.
Okay, let's try it. So then this turns into u is equal to e to the theta. Dv is equal to sine theta d theta. Du is equal to e to the theta d theta. V is equal to, I guess this turns into minus cos theta. Yeah?
Yeah, negative cosine theta. Yeah.
Yeah. So then when we do this out, this turns into sine theta minus I'm going to do many of these little calculations in my head, but the point is that it turns into what is this, minus e to the theta cos theta d theta. So at this point, we are coming across this integral right here, which is pretty much exactly the same as our original expression, right? So you might think that, oh no, we've run into a dead end, right? Have you seen a problem like this before, where your original integral popped out after a couple of integration by parts?
Yeah,
Yeah.
and then it's like copy. Like,
Exactly. You move it to the other side, right? It's the exact same thing, so this is actually really good, because then you just move it to the other side, and this turns into a 2, integral of e to the theta cosine theta d theta. And at this point, these are expressions that, are perfectly reasonable, and then you just have to divide by 2, right? And then you can isolate out the expression that you want, and you're golden. Does that make sense?
Yeah, that makes sense.
Yeah. I never learned a term for this, and because of that, in high school I was really had a hard time remembering it, because it's easier to remember things when they have names, right? But a German friend actually told me that in their language they have a name for this. They call this a phoenix integral, because you have the original integral, and then you see like a smaller version of itself rising from the ashes, so to speak, right? I think that's a cute little mnemonic to remember it. But the basic idea here is that if you see another one of them, check to see if that you can move it to the other side and get 2 or some factor of them. and then just divide by that factor. But that's very thematic. Okay. Are we ready for trig subs? Sorry, what's up?
And you can like only do that when it's like it has a negative sign in front of it, right?
Yeah, it needs to.
Because-
This is important. If it was a positive sign, we would be screwed, because then we would really be in a dead. We would be in a dead end. It would be a tight spot. But sometimes if it is a positive sign, but it has like a 1/2 or some other constant here, well, then you could still move it to the other side, because the constant makes it so that they don't totally cancel out, right?
Yeah.
Yeah.
Makes sense.
Perfect. Okay. Are we ready to take on trig subs? Do
We'll
we?
be back in like 10 minutes because it turns out the library is closing.
Okay, sure.
Feel free to start without me.
Sure. Understood. We'll probably keep going.
Yeah, no
But I
worries.
just wanted to discuss trig subs seem like probably the biggest challenge in this unit, right? Should I go
Yeah.
through and explain all the types of trig subs, kind of like integration by parts, or do you think it would be better to just hammer a bunch of problems through? What do you think makes the most sense? What do you think would teach you the best? What I can do is break down the various types of trig sub problems that you do see. Like there are like maybe 5 or 6 patterns that basically cover all of the problems you might see in this unit. And I think labeling them and breaking them down is probably pretty useful. But I'm going to ask you what you think makes the most sense. Do you?
Could you like do the same thing as like what you did for integration by parts, like explain
Sure.
all the
Yeah, of course. So, gosh, it's always this question of how the heck do you start motivating something like this, right? And the textbook essentially starts motivating it. Sorry, I just need to bring up my PDF because I had some really nice notes for this. 1 second. Okay, so for trig substitutions, where exactly does the textbook start? The textbook starts with the example of the ellipse, right? With the ellipse has some expression like x squared over a squared plus y squared over b squared is equal to 1. And they're basically saying, okay, let's see if we can figure out the area under the curve, right? So I won't do all the expressions, but I think y is going to equal to plus or minus the square root of b over a times the square root of what is it? Is it 1 minus x squared? All right, you move that to the other side. Yeah. So the idea here is, well, okay, let's just choose the positive. Let's just choose the positive half, and then restrict us to just one of the quadrants, and then multiply the final answer by 4. Right. But the idea here is that if we can just integrate y with respect to dx, we'll be able to figure out the area of this first quadrant. And that will let us calculate the area of an ellipse, which is something that we probably might like to know for some purpose or other. And the idea here is we're just staring at this, and we don't have any x outside, which is a shame, because then we could use either parts or u sub. So trig substitution trig substitution is something I understand as something someone very clever just pulled out of a hat and realized that 1 minus x squared looks a heck of a lot like a trig identity, like sine squared of u plus cosine squared of u is equal to 1. So 1 minus 1 minus sine squared of u is equal to cosine squared of u. And they just realized that if you just match this up, like this 1 and this sine squared, this 1 and this x squared, right? They just realized that, heck, you could replace what's inside here with a cosine squared of u, and the square root of a square is just a perfectly nice cosine, which is really, really tractable. That's the motivation for trig substitutions. Does that make sense?
Oh yeah, that makes a lot of sense.
Yeah. So like when you covered this in class, maybe the professor explained it in a different way, but I tend to think that a lot of students, I'm sure it went over my head when I first learned it too, but it felt like I just had this really, really weird integral pulled out of a hat, and they just put it in front of me and told me to solve it, right? felt like it was very cold and personal and just like an integral out of a vacuum. But this is the motivation for it. And the reason that people kind of thought of this equation in the first place is because the relationships between, circles and ellipses, they're kind of related to trig identities, right? That's the motivation behind this. And for this particular problem, it becomes pretty easy to solve. Yeah. This becomes the integral of what? B over A, cosine of u. You do need to figure out the du. So what is x is equal to cosine of u? No, I'm sorry. We set x equal to sine squared of u, correspondence to x squared. So x is equal to sine of u. And dx is equal to cosine of u du. Right? So then this substitution becomes cosine squared du. And do we know how to integrate cosine squared? I mean, I know how to integrate it. I'm just trying to test your recollection. Do you remember how to integrate cosine squared? What would you do in this situation?
I think you would use like the half angle identities, right?
Yes, exactly. That's probably the best move. The half angle identity is going to be your best bet here. So let me ask you this. Do you get to use an equation sheet or anything like that for your midterms?
No notes or anything.
That sucks. That really sucks. Because that basically means you're going to have I would say about 10 things that you basically got to memorize. Because you just don't have enough time to rederive them on the spot. Yeah, I'm sorry to hear that. But you're right that this does turn into 1/2 1 plus cosine of 2u du, right? And then this is easy enough to integrate because at this point, it's just one of them is constant and the other one is a cosine. And this is doable. So one thing that I would like to bring up for trig substitutions is when you are doing a definite integral, as I think a lot of these problems are, you have the choice of either changing the bounds of integration. So what's the original bounds of integration here, right? It's basically from x going from 0 to 1. So the bounds of integration for u is like an angle, right? U is an angle, so it's going to have different bounds of integration compared to x. I think u is going to go from, pi over 2 to pi over 2 to 1, maybe? Sorry, pi over 2 to 0, right? Because it's basically asking at what point, if x is 0, if x is 0, what is sine of u? Okay, I guess that's 0. And if x is 1, what is sine of u? Well, I guess that's pi over 2. I hate this personally. I think it's really, really confusing to have to worry about the bounds on an integral. And I prefer to just not even write the bounds in the intermediate steps and just plug them back in at the end. What I would do in this situation is I would integrate this to get myself b over a. This turns into u over 2. And this turns into, I think, sine of 2u over 4. Does that seem right? Sine of 2u. I just need to double check my math real quick because it's unfortunately a little bit important. For AB. Yeah, I haven't been very careful about my constants outside, which you would probably need to be on a test. I'm not a student. I'm not taking the class, so I don't have to be as careful. But every time you have one of these factors, you definitely got to make sure to keep track of where things end up. 1/2 1 plus cosine 2 theta sine 2 theta. Yeah, I believe this is right.
Where'd you get the u over 2 from?
The u over 2? This was because there was 1 times a half. The integral of 1 times a half is just the integral of a half, and that just turns into u over 2.
Oh,
right?
I see.
So what does this turn into? This turns into b over a, and then I would plug in x is equal to sine u at this point, which basically means that you got to draw a triangle. If u is the angle and x is equal to sine u, that means that, okay, sine u is equal to, okay, so it turns into x over 1, essentially. And this other angle would become Sorry,
1 minus
1 minus x squared. Yeah, 1 minus x squared. Right. Okay, so this is the... Yeah, sorry, this is the one of those... Yeah. And then okay, so this is typically how you do with indefinite integrals. I guess for this particular problem, it's a little bit easier to... Sorry, what does this turn into? Sine of 2u? Actually, you know what? I take that back. For this particular problem, it's a little bit easier to use the bounds of integration because it's kind of hard to... U at this point would be equal to like arc sine of x. And then you would have to do like sine of 2 arc sine of x, which is kind of miserable because the 2 and the arc sine, it's kind of hard to handle that. So, okay, for this particular problem, it might be a little bit better to just look at the bounds of integration and figure that out. Like, do you understand the process of figuring out the bounds of integration? Is that something that's a big point of confusion?
Yeah, could you go over that?
Yeah, sorry. Like, you can do it either way, technically. You can either plug it in at the end, or you could use the bounds of integration. But for, I guess, problems when you have to multiply the angle on the inside of a sine, I guess it's easier to keep it as an angle. So, okay. The original problem that I'm trying to solve is the area of the ellipse, right? And what I'm trying to do is I'm trying to split it up into 4 quadrants, and this is essentially varying x from 0 to 1, right? It varies x from 0 to 1. And it's essentially saying, okay, if x is equal to sine u, and x goes from 0 to 1, what does sine have to go from? And you basically just have to think to yourself, okay, if x is going from 0 to 1, then sine has got to be going from 0 to pi over 2, right?
Oh yeah, that makes sense.
Exactly. So then 0 to pi over 2. Like I said, I don't like thinking about it, but it makes it easier when you have to multiply u by some angle here, because otherwise you have to get into trig identities again. But this just turns into b over a times pi over 2, I think. Sorry, there was a... Is there 1/2 somewhere? I might have dropped a factor of 2, but I hope the idea becomes clear. Sorry, this should probably be a factor of over 4. Anyways, sorry, when I'm working it out on a screen, my handwriting is a little bit worse than usual, so it's hard for me to remember the factors, the constant factors. But do you see why the constant factors are just things that you can pull out and are relatively unimportant to the process of integration? Like, the fundamental problems that you're solving here are the integrals themselves, right? And the constants that, like 1/2 or a quarter, sorry, like the 1/2 over here, you can pull them right out without really changing the problem at all. But the point of this particular problem is to show you that, okay, if... Oh, shoot. Maybe I will just track down where the heck I dropped that factor of 2. That turns into a 1/2. Sorry. Oh, here it is. It's because this was u over 2, right? And then I plugged in pi over 2, so this becomes pi over 4. So then if you multiplied this thing by 4 to account for the fact that there are 4 quadrants to the ellipse, then you would get that... Wait, why do I have b over a?
It was like the original thing, like the original equation.
Yeah,
Where
my
you have
bad.
to
I
replace.
should have substituted something in slightly differently. I think I had sort of assumed that a was equal to 1 for this problem, unfortunately. Yeah, I was a little bit silly. I was basically... Sorry, I was a bit sloppy with my math here. Let's just say for this particular problem, a and b are equal to 1, because otherwise it would have to be the square root of a minus x squared. and you would just have to do a slightly different, you would just have to divide by a constant essentially. But the point is, for this particular problem, when a and b are both equal to 1, this just turns into the area pi r squared of a circle, and with radius is equal to 1, it's just pi, right? That's how you get the area of a circle. You get it through calculus.
Makes sense.
Right? And then, okay, when we, at this point, it's sort of just turning into a ton of other problems, right? Yeah, I'm looking through my notes a little bit, and at this point, you just have to basically scrunch a ton of problems. Is this something that's, like, I guess, where's your comfort level with trig subs at this point?
I think I'm okay with it. Like I've been doing a lot of it, so I think since I've been practicing a lot, I'm okay with it.
Gotcha. Let me ask you the question: how do you know how to tell the difference between when you're supposed to use tan squared plus 1 is equal to secant squared versus when you're supposed to use sine squared plus cosine squared is equal to 1? How do you tell the difference between these two cases? So if I gave you a problem like this, like 25 minus 9x squared, which one of these would you use?
Secant squared, or I would use the secant squared one, because if you like move the if you move the tan squared. Oh wait.
I just got.
Oh wait, you use secant squared one. Or
I thought it would be 1 minus sine squared.
Yeah, for this one, I would say 1 minus sine squared. 1 minus sine squared equals cosine squared. Like, it's tricky, right? But if you tried to do it this way, you basically need to match up. This is constant sort of needs to become your 1, and this sort of needs to become your trig value. So this turns into 1 minus sine squared is equal to cosine squared is a bit of a better match, because if you tried to do 1 minus secant squared, that would give you minus tan squared, right? And you would be taking the square root of negative tan, which doesn't make much sense.
Oh yeah, I mixed up my words.
Yeah, no, exactly. It's totally cool. You basically, for these problems, I would not memorize the table in their textbook. I would instead just always look at tan squared plus 1 is equal to secant squared, and sine squared plus cosine squared is equal to 1. That's what you always, I think that's what you always should go back to. Right? I think it's a much better idea to go 1 minus sine squared. Sorry, it's a much better idea to memorize this rather than like all the permutations of constants and variables. You would always just want to go back to pattern recognition and see if you can make them match up. Yeah. And for this particular one, some people like to just try to figure out what value of x. So like, I guess for this particular case, x is equal to, sorry, u is equal to, what does this even turn into? Like, I hate doing, some people try to make u equal to like 3x over 5, I think. Is it the other way around? Sorry, they basically say 9x squared is equal to u. Like, I hate doing it this way. What I always like to do is I like to pull out the 25 first, right? I always like to make it equal, so that 1 minus 9 over 25 x squared is what you get, because I recognize the 1 from the sine or the tangent expression, right? So you always match it up like this. The 1 over here, and then the x over here matches up with something trig. And at this point, it makes it extremely clear that sine squared of x is equal to 9 over 25 x squared. Sorry, I should call it sine squared of u is equal to 9 over 25 x squared. And from this point on, you can handle the problems, right? But other people, and I think in the textbook, they like to try to figure out what the substitution should be even before they pull this out. And personally, I think that's kind of a pain. They basically try to say, okay, 25 should correspond to minus 25 sine squared, right? So they basically do like 25 sine squared of u is equal to 9x squared. And they try to look at the substitution like this instead. You know, you can pick your poison, right? It should be ultimately the same thing. But I just think it's a lot easier to recognize when you make sure to make the constant equal to 1. Because I think a pretty common failure mode is when people look at this and think to themselves, okay, is it the 9 that I should be bringing down to a 1, or is it a 25 I should be bringing down to a 1, right? Because an equation like this, both the 1 and the sign have coefficients of 1, so it can be really confusing how you're matching it up. You see what I mean? When there's two different coefficients here, but the coefficients here are both 1, I think students like to get tripped up a lot, and someone actually told me on the previous quiz that's where they made a mistake. Do you see what I'm getting at?
I see.
Yeah, I
So
see.
you'd make it 1 and then you divide and then take out.
Yeah, I think it makes it really
gotcha.
clear that this 1 is kind of your North Star, right? You need to make this 1 to match up with a trig identity, but then the sign can, absorb up like an extra fraction part, like 9/25. That's how I like to think about it. But yeah.
Oh,
Mhm.
yeah, this makes a lot more sense because, or it's like the way they taught us was that you would like make the 25 into like 5 squared, and then 9x squared would be like 3x.
Mhm.
Yeah, and then like you would set like the u, so it'd be like u is equal to sine, or like a sine theta or something. Yeah, it's
Yeah,
something
exactly.
very complicated, but
Like-
this one is like way more intuitive.
Exactly. I really hate putting an A in front of the sign. That for me, that's very hard to see. I like saying, excuse me. I like seeing the sign kind of. I can put all the complicated fractions I want in front of the x. That I find easy to grasp as long as the sign is on its own. Because then once we substitute this in, this just becomes 1 minus sine squared of u, which is just equal to square root of cosine squared of u, which is equal to cosine of u. It's really nice, right? I think it's really, really nice. Right. At this point, I think that's sort of the big idea behind trig substitution trig substitution is the very first step of the battle is figuring out the 0th step of the battle is figuring out if you want to use trig sub in the first place. There's a good number of problems where I would say it's easier to use u sub or integration by parts. Like if you saw this problem, right? If you've been looking at way too many trig sub problems, you might immediately think to use trig sub, like tan squared plus 1. But really, this can be your u, and this can be your du, right? And that's going to be a lot easier. So part of the challenge in this section is figuring out which one of these you actually want to use, right? But I would say first try u substitution, then try integration by parts, and then if you must, go to trig sub. I would say it in that order. And sometimes if it's just, sometimes it's just very obvious that you have to go to go to trig sub. Like if it's just something like 1 over, 1 minus x squared, there's just no way, right? All you have is this really complicated term, and it looks a lot like trigonometry. So yeah, in that case, go jump to trig sub. But the point that I want to get across is that you should keep your eyes open if there's an easier path available. Because trig sub is doable, but it's tedious and kind of hard, right?
I see.
Yeah. So at this point, I think without further ado, I would probably just go through each of the types of trig sub problems. Yeah, there's like 3 or 4 different types that you can handle. Do you have any other conceptual questions before we hit that? I realize that
don't think I have any.
What's up?
Oh, I said I don't have any more questions.
Sure. I guess I should have, maybe I'm sort of doing the trig substitution problems before I'm doing the trig themselves, but you can sort of do them in either order. They're surprisingly different, I would say. Okay, so I guess that was the first type. This was the first type where we had a constant minus the x squared, which ended up being the sign identity. Just rearrange it. Now we have something like 25 plus x squared dx. And which identity would we want to use for this? Sorry, tan squared plus 1 is equal to secant. Which identity do you think we should try out here?
Tangent?
Yep, I agree. So I guess I wrote them backwards here, but it's not really a big deal. But the 1 corresponds to the 25, and the tangent corresponds to the x. I guess I'll call this tangent of u. So like I said before, what I like to do is I like to pull out the 25, and I like to make this 1 plus, I guess this just turns into an x over 5 squared, right? And this corresponds really nicely. And I think if you write it out this way, it's really, really hard to go wrong because you see how clearly the tangent has to correspond with the x over 5. So this point, tangent of u is equal to x over 5. So what's the derivative? It turns into secant squared of u du is equal to dx over 5. And if we start, sorry, there should be dx here. If we start subbing these things in, what do we get? Well, 1 plus tan squared is secant squared. So I'll bring the square root of 25, which is 5 outside. So this just turns into a secant of u, because this is a square root of secant squared. And then this turns into a secant squared u du times 5. Right? Because the 5 moves over to the other side. So I think this turns into a 25 secant cubed u du. Do we know how to do secant cubed? A lot of these things are kind of annoying, but
You like break off one of the secants, right? And then it becomes secant squared times secant, and then
yeah, that's probably what I would recommend. Unfortunately, this is not quite as nice as you would hope because, wait, how many do you want to break off? If we broke off a tan squared, 1 plus tan squared. What's up?
yeah, that's what I was gonna do.
Right, and this turns into a secant of u du. Yeah, problems like these are always a tiny bit nasty, and you can probably look at your trig sub techniques, but it should be doable, right? Because the secant is, I believe it's on its own, whereas the tan squared u times the secant u, let me double check. I think this is very manageable, but I want to double check the idea. Even power on secant, odd power on tan. Maybe that's not the best technique. Yeah, it's always a little bit nasty. Questions like these always take a little bit of creativity. What would we do with secant cubed? Oh, I'm sorry. This is can we just do? No, this one is actually surprisingly hard. This is not one of the basic integrals. Yeah, this is an integration formula, in fact, which is not very nice at all. But this is considered, yeah, now that I'm looking through my notes, secant cubed of u is actually considered a pretty fundamental integral in the sense that it's very hard to solve, but most textbooks or sources provide it. But you don't actually, I'm pretty sure you'll never get asked to do something this nasty on the spot, but it's equal to this. I don't personally know the derivation. This unit is just kind of nasty in that there's a couple of handful of things that they just assert are true and don't show you the proof for them. And it turns out that secant cubed is one of those handful of nasty things. But the point of this problem was to get across the cancellation over here. Sorry, the point of this problem was to go through this process over here and show you how to do the replacement. That's the most important part of trig subs. If it's, a 50-minute test and there's 13 or so problems, I can't imagine that they're going to make any of these too tough. You're probably not going to get some incredibly involved thing. I think it's just a matter of finding the right matches and substituting. Gosh, this is what I mean when integration is so much harder than taking derivatives. Because with derivatives, you can there's like a procedure for just about every elementary. If you have a function combined of a bunch of regular things like cosines, sines, ln's, there is some procedure to do it. You know what I mean? But with integration, it takes trial by error, sometimes a bit of luck, and just all around a bit of ingenuity. And unfortunately, that's just how integration is. They sometimes have integration bees at various universities where they just have these ridiculously hard integrals that the people try to solve in like competition formats. They don't have derivative bees because derivatives are relatively clean. Sorry, I shouldn't say clean, but relatively straightforward. But are you sort of understanding the difference, what I mean? Like, I don't think, you probably never had a case in single variable calculus where you're just like, I have no idea which technique to, like, what I mean. Once you knew all of your techniques and the order to apply them in, there should be very little ambiguity in calculus 1 to take a derivative. Does that sound familiar?
Yeah, it seems like there's like a bunch of different choices that you could take. For
Exactly. You
integrals.
basically have to figure out the right choice to match up with the thing that you have. You have to figure out how to simplify it to make it look like one of the existing tricks. And that process is sometimes really, really hard. Okay, so for a problem like this, what would you do? Which one would you use? It's always good to just go through some of these examples so that you're very confident.
Tangent?
Yeah, I would say so. So then the -1 goes to the other side, right? So tangent squared is equal to secant squared minus 1. And if we were to match these up, this would look like secant squared minus, okay, well, we're probably going to want to pull this out, like I said before, because I like it when it has a 1. But this is going to look like x over 2 squared. So always be careful. The only hard thing about the way that I like to do it is that you just have to be sure that when you're dividing through, you get the right number inside the square. You know what I mean? Like, a lot of students might be tempted, if they're not being careful, to write a 4 down there. But because it's being squared, it's really only a 2. You see what I mean? But this should turn into secant squared minus 1, which means that secant of u is equal to x over 2. And therefore, the derivative of secant, do you know what this is off the top of your head? Secant is one of the handful that you have to know.
I have I just looked it up in my notes. Isn't it like ln of tangent x?
That's the integral. That's the integral. What's the derivative of secant?
Derivative.
Secant x tan x?
Exactly. Secant u tan u du is equal to dx over 2. So hopefully things will be quite nice. This root 4 just turns into a 2. Well, x in the bottom is just 2 secant of u. And this square root turns into a tan of u, right? It turns into a tangent. Secant squared minus 1 is a tangent, right? So, and then the square root turns it into a tangent on its own. And then you get a secant of u, and then you get a tan of u and du, because the dx gives you all that. So at this point, we have just the integral of tangent squared. Du, right? And do we know how to do the integral of tangent squared?
Oh yeah, I do, but I forgot.
Yeah. So tangent squared, even powers of tangent are really, really handy. So this is one of the cases. So even powers of tangent are really nice because you can turn them into secant squared of u minus 1. And remember, this minus 1 is obviously really nice. But what can you do with secant squared? How do you what's the integral of secant squared?
Tangent?
Exactly. It's perfect, right? These trig substitution integrals are kind of nasty because you're jumping all over the place. But in some sense, they have this weird elegance where they always, we bounced around here from what is it? We had a secant, it turned into a tan, all this other stuff on the bottom, right? And then we get a tan squared, and then it turns into a secant squared, and then it turns back into a tan. You see how we're getting bounced around all the time? But there is a sequence to it. And that sequence is important. So this turns into tan of u minus u plus c. And to just do a quick example of what I mean by drawing the triangles. secant of u is equal to x over 2. So secant is 1 over cosine. So this means this is x, and this is 2, and this is x squared minus 4. So the tangent of u becomes square root of x squared minus 4 over 2. And u, there's a lot of choices for it. We can express it as the arc sine, arc cosine, or arc tan. We have a billion options. I'm going to express it as the arc cosine of 2 over x. What I was saying earlier about for definite integrals, if you don't want to change the bounds, you can wait till the very end until they turn all the way back into x's. Right? So if you had some, x from, I don't know, 0 to 1 over here, or I guess 0 to 2 over here, if you wanted to, you could change the bounds in the halfway, because x squared minus 4 is kind of a circle with radius 2, or maybe like an ellipse with radius 2. So you could change the bounds from 0 to pi over 2 if you wanted, but personally I would just prefer to ignore all that in the middle and then just evaluate it at the very end for x equals 0, x equals 1, or x equals 2. You see that? This is not a good one because 0 is undefined here, but hopefully you see what I mean. So
Yeah.
I guess it has to be a minimum of 2 because it's subtracting a 4, right? So let's say from 2 to 3. But the idea is you can always look at your triangle at the end and then just plug in your bounds afterwards.
Mm-hmm.
Make sense?
Makes sense.
So these are basically your trig problems. Have you seen any trig identities that look like this before? X squared plus bx plus c. Do you know what you would do if you saw this situation? Because
Would you like factor?
yeah, okay, that's pretty good. What exactly do you mean factor though?
Like,
Let me give you an
break it up
explicit
into
example.
three.
Yeah, let's say x squared plus x plus, would this work? Let's say x squared plus 2x plus 2. Okay. What would you do in this situation?
Would it be x plus 1, x plus 2? Or
You
Actually,
can't factor this cleanly in one go, unfortunately,
God.
but it's a valiant effort. I would suggest putting this in terms of completing the square and see what you get. Right. The nasty thing about this thing right now is that we wish it was just x squared and the constant, because then we could use one of our trig identities, right? But there's this nasty thing over here that's kind of getting in the way. So the idea here is, what if we can express this in terms of some other perfect square? Oh, or sorry, can we complete the square? And what I mean by that is, okay, x squared plus 2x plus 1 would be a perfect square, right? Because that's just x
Yeah,
plus 1 squared. So the idea is you just do what they call this adding a smart zero, right? Plus 1 minus 1, because this is exactly the same thing as before. It just looks a little different and makes it clear why we can sort of come up with a perfect squared in here. But this turns into x plus 1 squared plus, well, this 1 now gets bunched up, so this negative 1 has to go with a 2. So this just becomes x plus 1 squared plus 1. Right? And at this point, do you know what you would do? It starts to look a lot like a trig sub, right? It just is a tiny bit nasty. What would you do? We know how to do a problem like this, right? We would know how to solve this using our trig subs. So how would we solve this?
would you do a U sub?
Exactly. You got it. Use substitution to replace it. And then from that point on, it turns into a trig sub. So at this point, you should be able to handle, I think, just about anything that's under a radical. You might get other problems that have it. It doesn't have to be a radical, right? It could also be to the 3/2 power. You might see that quite often, right? Because
Yeah, I had something like that in my quiz.
exactly, if it turns into a 3/2 power, it's not that different, right? Because the goal out of one of these things is to get a cosine squared or a tangent squared or a secant squared underneath there. So the square root of something squared is just the regular tan, but then the 3/2 power of something squared just becomes a tan cubed, right? So if this became like a secant of u, right? This thing over here would become a secant cubed of u. It's not too different. And hopefully they set the problems up so that you will get something nice and not too nasty. But I would say that that's basically your three kinds of trig substitution problems, and really they're not all that different. I would say every single time what I would do is personally just write out the two identities, sine squared plus cosine squared and tangent squared plus 1, and see how to massage it so that it matches up, right? The lessons here are you might have a coefficient in front of the x, you might have a the constant be something greater than 1, but you can always just you can always just factor this part out until it becomes a 1, and then compare it just by visual inspection to one of these expressions, right? Just, this is thematically what I would do every single time. Okay, so I guess step 0 is complete the square if you need to, and then do a u sub. But after that, if there's a constant here like a, then I would pull the a out and compare it to our sine squared identities and tangent squared identities. And that's the recipe to do every single one of these substitution problems. They start getting really repetitive. But that's the idea. That's the hard part. That's the hard part that I can talk about. The other hard part is just going through the crunch of, a couple of patterns. Because sometimes you get really nasty questions like, how do you do, I don't know, like tan squared of secant or something like that. Like there's all sorts of patterns that you just have to spend like maybe an hour a night practicing for. But this is how you get to the setup. This is how you get it to the point of a computation, right? Is this feeling okay?
Yeah, everything makes sense so far.
Okay, very cool. So we did trig substitutions before regular trig problems. Do you want to talk about trig problems really quick and like identify the 3 or 4 patterns there?
Sure. Yeah.
Okay.
I think the ones that were really confusing on the trig problems are like the tangent and secant ones, rather than just like the cosine and sine ones. At least for me.
Yeah, I see what you're saying. I do think it's probably worth just going through an example, one of each pattern. But
Yeah, definitely.
let's say that cosine or sine, one of them has an odd power. So cosine or sine is, one of them is odd. So how would you do something like this? So sine squared of x, cosine cubed of x. What would you do here?
You would like break off one of the cosines, right?
I agree.
Or
And why the cosines rather than, I agree with you totally, but why the cosine rather than the sine?
because the cosine has an odd power.
Exactly. The idea here is that cosine, if you broke it up to like cosine squared of x times cosine of x dx, sine squared of x. Okay, well, cosine squared we can convert to sine squared using an identity. So this turns into 1 minus sine squared of x. And the idea here is that, all right, if we look at it, all of these things, we can multiply them together. And at this point, it's all going to be a bunch of sines, right? It's going to be sine squared minus sine to the 4th. And what we're left over with is cosine of x dx, which is a really good candidate for u substitution, because if we let u be equal to sine x at this point, the du is going to be cosine of x dx. This cosine of x is really perfect for like absorbing the effect of the chain rule, right? It's I think it's really elegant actually. But the the clear case here is when it's an odd power, you can play around with it a little bit, but the idea is that you can always break off these factors, these cosine squared factors, until you get left with just a cosine. Then you convert all the even powers of cosine to sines, and then you would just be left with a nice U substitution. That's pattern number 1. Not too bad, right?
Yeah, that was pretty simple.
Yeah, exactly. And this would totally work if sine was to higher powers and cosine was, to the 5th power or 7th power or whatnot. And sine doesn't even have to be there, right? It could have just been cosine cubed of x. You would have done this much the same way. This just would have been 1 minus sine squared times cosine of x. And at this point, it would turn into cosine of x on its own, which is easy. And then sine squared of x times cosine of x, a perfect candidate for U sub. Okay. We already talked about
So
cosine.
essentially,
Mhm.
you're always supposed to make the power into 2 so that you can use what are the identities, right?
Yeah, exactly. Whenever you have a power of 2 for sine or cosine, you can break it down. You've seen the reduction formula, right?
I
Yeah.
actually don't.
Aren't
Wait.
those used on some other specific sine and cosine problems, right?
Right. There's candidates for. So I think the reduction formula was this particularly nasty expression in your textbook. It's basically if you have a very high power of sine, it shows you how to rewrite it in a slightly lower power. That's all it is. It's nothing crazy. But the idea here is that sines and cosines kind of jump in powers of 2, if that makes sense. And because they jump in powers of 2, and you would really like to get just a single 1 left over at the end, that's why odd powers of sine or cosine are so easy to work with. Does that make sense? You want a single power left over at the end for chain rule purposes. So then if everything else is, so if everything else is even, plus this 1 over here, that means, it's these odd powers that are solved this way. Does that make sense?
Yeah, that makes sense.
Yeah.
Cool. Okay, so now we get to secant and tan, I think, right? And oh boy, these are the ones that give everybody trouble. But so it's even powers of secant that we can handle. So if we have a situation like tan squared of W, let's make it even nastier. Let's make it tan to the 4th or maybe even to the 5th of W times secant to the 4th of W dW. So the idea here is, okay, we use trig identities. Even powers of secant, we know that the derivative of tan is equal to secant squared, right? Secant squared x dx. So similarly to the sine and cosine situation where we needed to have a spare cosine or a spare sine to absorb the chain rule, here we need to have a spare secant squared to absorb the effect of the chain rule. Does that make sense? It's almost like, what do you call it? It's almost like, think of it almost like a down payment, so to speak. You're trying to buy a house or a car or something, and for some weird reason your boss only pays you in even quantities or something like that, and you need to spare a certain amount for a down payment for the car, right? So you need to keep a secant squared dw reserved as sort of your down payment, but then your other stuff is like secant squared w and tan to the 5th w, and the secant squared can be turned into a tan using one of the identities. So at this point you have a polynomial. You have something that looks like a polynomial. It's just a bunch of different tan terms, and then a bunch of secant squared, just a single secant squared w over here as a chain rule. Do you understand what I mean? You're kind of like reserving, you're kind of thinking about your chain rule ahead of time to make sure that whatever you come up with kind of folds perfectly into that chain rule. You see what I mean? This tan 5th w, and this is 1 plus tan squared, right?
You're just always
Yeah.
trying to reserve out a secant squared.
Exactly. If you can reserve a secant squared and your boss only pays you in terms of tans, well, that's perfect. Because every one of these tans you can U-sub and then get a chain rule secant squared out of it. You see what I'm saying? I don't know if this analogy works, but you have some crazy boss who only pays you in terms of tangents.
If it was like a secant to the fifth or something,
Yeah.
how would that work?
That's where we might struggle a little bit. We don't generally. So the way that I understand these problems is that we can't solve everything. Like there are some combinations of secants and tans that we're just basically powerless to do, right? And it seems to be even powers of secant that we have some control over, or odd powers of tan, and I'll show you why in a second. But like if I generally had some expression to like just integrate secant to the fifth w dw, this would be really bad. This would be really bad. Because what does this become? Right, this, if you were try to reserve a secant squared of w dw, and then you get left with secant cubed. Okay, well, I don't know. What can we do with this? We can try to turn some of these into a tan and a secant of w, but there's just, I don't see any good way to handle this. Maybe some miracle happens if we try integration by parts, but I can't guarantee you that there's a solution here when there's a odd power of secant. So now let's look at the other rule, which is even powers. I'm sorry, it's odd powers on tan. And the idea here is if you had like, I don't know, tan of, let's say tan of 3, and then secant of, I'll use an odd power of secant here because I'm trying to get across the point that it doesn't matter. Right, earlier I said if you had a odd power of secant, I can't generally solve it, but for specific cases where the tangent is nice, then I can solve it. Does that make sense? I'm not saying that an odd secant is unsolvable. It's just that this particular one is solvable because tan is nice. You see what I'm saying? It's either an odd tan that's nice or an even secant that's nice. Does that make sense? You're kind of taking...
So more so it just depends on the problem, pretty much.
Sorry, how would I word this? So you sort of have a... I'm trying to draw like a union, but I can't exactly visualize it super nicely. The point is that if the tangent is nice and odd, then secant doesn't matter too much. If the secant is nice and even, then the tan doesn't matter too much. Roommate is playing Valorant. But the idea here is that tan cubed of x can be split up pretty nicely because okay, the thing that we're trying to do here is using substitution for u is equal to secant of x. So du is equal to tan x secant of x dx, right? So
you're trying to like take out like one of each? Exactly.
That's why tan has to be odd. I guess the secant you need at least one of them. But all right, so let's like before, we're reserving a bit for the chain rule. Yeah. So we reserve a tan x and we reserve a secant x dx, and we're left with tan squared. And we're left with secant squared, secant to the 6. Yeah. So, okay, we know we want our u's to be secants. So this means that instead of in the previous problem, we turned the secant into a tan. Now we want to turn the tan into a secant, which is totally cool, right? That's the exact same identity. Is it secant squared of x minus 1 times secant to the 6x, right? And then tan of x, secant of x, dx. You see how perfect this is? This is just going to be secant to the 8th minus secant to the 6th, a bit of u substitution, and, you know, it looks like every normal polynomial that you've known how to do since day one. You see that?
I think so.
So you're
Should I write one more step just to make it a little more clear?
I see what's happening. I didn't see the tangent x, secant x. Okay, yeah, that makes sense.
Gotcha.
So you're putting it all and then you're u subbing. Yeah, no, that makes sense.
Exactly. So this turns into a u to the 8th. This turns into a u to the 6th. And then this tan secant dx is my du. So it's just perfect.
I see. Yeah,
That's
no,
the
that
idea
makes a
behind
lot
these
of sense.
problems. Exactly. So, like I said, let me try to like draw a diagram here, right? You have is a Venn diagram the way to make sense of this? Or so you have problems with sorry, I'm trying to remember. Is it even secant? Even secant and odd secant. And then you have even tan and odd tan. I'm saying that even secant problems are really nice. And I'm saying that odd tan problems are also really nice. So problems in this quadrant, you can do either way. Problems in this quadrant, you got to do one way. Problems in this quadrant, you got to do the other. Problems over here, you're just screwed. But the teacher's not going to ask you one of those.
Okay, cool.
Does that make sense?
Yeah, that makes sense.
Gosh, I really hope that the professor just isn't some sadist who, you know, throws in one of these problems that just happens to have some absurdly clever trick. But on a 50-minute test, we're just going to have to hope that that's not the case.
Yeah, usually the quiz and the exam problems are pretty similar to the lecture problems, which usually aren't like bad. But sometimes the issue just with like the midterm, at least the last midterm, is that like it's so easy to make one little mistake.
I know.
And she puts like, it's not like a 4-answer thing. She puts like 7 answers, and then one of the answers is an answer not on this list. So it's not really a multiple choice.
I see.
I guess.
That's terrible.
It's
This is just some terrible format.
yeah,
I'm sorry to hear that.
It's weird. It's weird because all of the quizzes are not like that. All the quizzes are like partial credit you can get and things like that. But it's just very stressful.
I hear you. Like, damn. Would you say that this is a class? Like, do they tell you the averages? Because that sounds absolutely brutal.
I don't think. I think if it's like if the class average is lower than like 50 or something or 75, I think they curve it. But I don't think they tell us like what everybody did on like the exams. I don't believe.
Gotcha. Good to have you back. Did you happen to listen in on the explanation for the secant and the tan? Sorry, I think the even powers of secant.
Sort of.
Or
I
sorry,
like heard somewhat, but I was like too busy just looking for an available space.
Okay. Well, I don't think it. I think this is important stuff, and I don't mind going over. Going over it again. But so even secant, we were sort of reserving the secant squared. Sorry, the reason even secants are nice is because we're sort of reserving the secant squared, and then all the other secants that are because we said that it's even, right? We took out a power of 2, so what remains is still even. And by using the secant squared laws, we can transfer all of those over to tan. So at this point, we're just left with some polynomial expression of tans. Do you know what I mean by polynomial expression? This is just a bunch of powers of tan added together. Right?
Makes sense.
And then all that's left is secant squared WdW over here. So this is a perfect U substitution.
Oh, and then you just like took out another, or you took out a secant so that it'd make it like even or something?
Yeah. So this is the part that we reserved for the chain rule, right? And because the initial hypothesis was that this is the even case of secant, well, all of these secants, because it's even, we took out 2 out of an even number, so what's left is still even, and we can transfer all of these over to tans. And at this point, we just have a bunch of expressions of tangents, right? And this is a perfect candidate for U substitution. U is equal to tan, du is equal to secant squared. Right?
Oh yeah, I really see. Yeah, I see how perfect it is.
Exactly. It's perfect. Yeah, it's just contrived for you to be able to solve it, essentially. So then we have odd. So that even powers of secant are nice because secant squared is the derivative of something, which happens to be tan. Odd powers of tangent are nice. I should say odd powers of tangent with some secant. I think you need at least one secant to do this, right? But the idea is that, okay, if you have at least one odd power of tan and if you have an odd power of tan, you can take out a tan and you can take out a secant because tan secant is the derivative of secant. Yeah? So at this point, you just want to convert all of your stuff over to secants. And because my initial hypothesis was that the power of tan was odd, you took out one power of tan, so what's left over here has got to be even. Which means you can use the squared formula to convert everything over to secants now, right? Now everything here is just a big bunch of power of secants, and U substitution works out perfectly again. See that?
Oh yeah, I see that.
Yeah.
So you take out one of each, right?
Sorry. Yeah, you basically take out one of each. You reserve one of each for the what do you call it, for the chain rule?
Or chain rule, yeah.
Right. But the point is that the power of tan for this particular technique matters because we need a perfect. Okay, so you take out one power of tan, and we need this to be even in order to use the tan squared rules to convert them all to secant. It doesn't really matter what the secant power is for this technique. You see what I mean?
Oh yeah, I see. Because
Yeah.
you're just gonna turn all the secants to, or all the.
Well, we're just
Yeah.
solving the
Okay, it
secants
makes
directly, basically. We're using U
Yeah.
substitution. Yeah, if this was a 7, then this is a 7, then this is a 7, and that's a 9. No big deal, right? But if this tan power was even, if this was a 4 instead, and you took out a power of 1, then you're left with 3. And because it's an odd power, we can't convert all of the tangents into secants, and then we're screwed. So I essentially drew a diagram over here. I'll draw it a little bit neater, but it's basically even tan, odd tan, even secant, and odd secant. And what I believe is the case is, okay, if you have an even secant, that's great, you're good. If you have an odd tan, sorry, I guess I should shade it this way. If you have an even secant, that's good for both these cases. And if you have an odd tan, you're good for both these cases as well. So I think cases over here, you could solve either way. Cases over here, you would have to solve using the odd tangent method. Here, you would have to solve using the even secant method. And for even tan, odd secant, I think you're just screwed. I don't think we know how to do that. And I think that's a pretty good summary of what you're expected to know from Trig Sub. Again, just to write out the do something similar for even and odd sign. Odd sign, even sign, even cosine, even sign. Odd sign you can solve really nicely using the by reserving one of the signs. And I'm sorry, what did I write here? Even sign, odd sign, even cosine. I should say odd cosine. Sorry, my handwriting isn't very nice. Odd cosine you can solve in a similar way. But for even cosine and even sine, you might not be powerless. There might be some reduction formulas you could use for this case. So for this case, I would say...
yeah, we learned about the the power reducing.
Exactly. So maybe look at the power reduction rules in your textbook to see... Okay, don't quote me on this, but I'm pretty sure that any power, even if it's both even powers of secant and... powers of sine and cosine can still be done. You just have to get creative with the power reductions or whatnot. I highly doubt that they're going to ask you something like that in your exam. But there's also, you can also use the double angle formula, which is basically just another form of power reduction, right? They're very similar.
Yeah, we learned about the power reducing one, but I don't think we ever went over the doubling.
Oh, the double angle formula? I mean, that's something that ideally we would know from, pre-calculus, but I forget it every time. So cosine 2x is equal to cosine squared of x minus sine squared. And because sine squared and cosine squared add up to 1, we can replace this by saying 2 cosine squared minus 1, or 1 minus sine squared. So this technique essentially gives you a way to convert a square. Sorry, this technique gives you a way to convert a square of cosine or a square of sine into a cosine of 2x. So you get to bump it down by a power in return for making the argument double.
I see.
Make sense?
Yeah.
Yeah. Hopefully not too bad. Actually, let's see if during your practice problems. I realize we're coming a bit to the end here. I hope this is productive. I think I maybe got off to a bit of a rough start with the trig stuff, but I hope the stuff towards the end was helpful at sort of laying out what you can and can't solve.
Yeah, it definitely makes a lot more sense.
Right. I hope going through these things case by case makes it very clear what you have power over and what you don't. And once you understand what each of these cases are, there's a prescription to handle them. And I think that's great. I hope, are the two of you both feeling pretty good about partial fractions?
I think there was a more complex version. I'd have to look over it. Basically, we had last week, we haven't we went over partial fractions in class. There's 2 or 3 other sections that are supposed to be on our midterm that we haven't even covered yet. So yeah,
Interesting.
I haven't looked at those yet because I've been really busy.
Right.
And I haven't really looked too much into the partial fraction one yet. But I believe I know how to do it the basic way, but there's a more complex way, and I can find it in my notes right now.
Yeah. So partial fractions are something that we all learned in high school, and I think most people have forgotten. But it's something you basically just got to brush up on because they make it's really, really hard to integrate stuff like 1 over x squared plus 3x plus 1 directly. But if you can break this up into partial fractions, into linear terms, you have total power over that. But the idea is that partial fractions, it's some algebraic law that any proper partial fraction where the degree of the numerator is less than the denominator can be broken up into either linear terms like x minus a, or irreducible quadratic terms like x squared plus cx plus d. And both of these you more or less know how to do. This one is just easy. This just turns into an ln of some sort. And stuff like this you can probably handle with trig. But, go through the textbook. It's a bit of a slog, but it should just take you half an hour to hopefully brush up on partial fractions. And and then after that, they should be the easiest type of integrals from there on out.
Yeah, it was the x squared ones that was supposed to be the more complicated.
Yeah, exactly.
X minus a's are pretty easy.
Exactly. Sometimes you have these things to a higher power, maybe. In which case, there's a special procedure for those. Right? If you had something that looked like, let's put this all over 1 fraction. I think the prescription for this would be something like 1 over x minus a. 1 over x minus a squared. Sorry, I guess it's a over this, b over this, c over x minus a cubed. And then it's something like, oh gosh, it's so messy, cx plus d, or dx plus e over the quadratic. And then yet another, I think, fx plus g for the quadratic squared. But it's basically, I think, 4 cases. It's whether or not there are powers. Sorry, it's whether or not they're all linear, or if there's some quadratic. That's one of the decision branching points, and the other branching point is whether or not they're all to the first power or some of them are to a higher power. And from there, these problems are basically just a crunch. But yeah.
Yeah, I'll have to look over this.
Yeah.
I'm planning to look over all the rest of the stuff today.
Exactly. Like partial fractions should just be a crunch that you got to spend like half an hour to review. But I think most of the hard parts are, so much of this stuff is super mechanical. I've shown you today how to break basically everything down into a very procedural way. And I think the only really difficult things that should be left is when you do trig substitutions and you get some crazy expressions of like secant squares over maybe tans or something like this. Every now and then you have one of these integrals that's going to be a little bit tricky, but on a 50-minute test, I can't imagine they're going to put anything like that on it. Do you know what I mean? Like sometimes you have problems that look like 1 minus 1 plus like 9x squared or something. And then it's going to be like over x cubed or something, dx. So when you let x be equal to tan, you're going to get a bunch of tans down here, and you're going to get a bunch of like secant squareds from the derivative. And hopefully they all cancel out really nicely. But on some of the harder practice problems, they might take a bit of massaging to work out nicely. I would say that's the only like... That and maybe some of the splitting for integration by parts would be the only tricky things you'd have to worry about. I want to give you a cheat sheet. Like, not to cheat, obviously, but a cheat sheet for the purpose of every big identity that you want, because there are like about 12 things you need to memorize. The noble, math student in me wants to say, oh, you can remember everything. Or, sorry, you can... learn how to solve everything for yourself so that you don't have to memorize. But this is a 50-minute exam, right? So I would say you are screwed if you're trying to rederive some of these identities. Here, let me basically write them right here so you can copy them down if you want and make sure you have them memorized. But I would need you to know the derivative and integrals of sine, cosine, tangent, CSC, secant, and cotangent, right? Now these ones I feel like you should... Okay, I don't actually... There's a couple of exceptions to these. I don't think you need to know the integral of... Okay, so I'm going to write the... I'll write a derivative if you need to know the derivative, and I'll write an integral if you need to know the integral, right? But this you need to know the derivative of. I don't think you need to know the integral of tan. I don't even know if I know the integral of tan. But derivative and integral. I would say you do need to know the derivative and integral of this one as well. And then just the derivative. Remind me, am I crazy? Have you ever seen the integral of tan or cotan before? I hope not.
I think I
so.
might, maybe. I'm just looking at my notes right now. There are like two integrals. I know we have to know like the integral of like secant, and I feel like it was tan. Or it was something similar to tan.
Yeah, secant and cosecant, they basically just give you. If I remember correctly, those are some fairly complicated integrals that are just a total pain in the butt. And I think they just tell you what it is instead of proving it to you.
Yeah, we're just like told what it is. Trying to see if I have it. I have it somewhere in here. I'll find it quickly. But I know I need to know the secant one. I feel like I do need to know the tangent one.
Okay.
Just give me a moment. Let me just...
Sure, okay. I'm just going to keep writing down the other things that I am aware of. 1 minus cosine squared of 2x. I would say sine of 2x is equal to 2 sine cosine x. And I would also say the product identities. Do you remember the product identities? They're in your textbook. Not every calculus class cares about these, but it seems like yours does.
just hit the button here really quickly. Yeah, we need to know the integral of tangent and secant. So the integral of tangent is negative ln cosine x plus c, and the integral of secant is ln tan x plus secant x plus c, which is something.
Yeah. Actually, the derivative, I'll make another point. The integral of tan and cotangent are actually not that bad, and you could probably rederive these on the spot. Because sine and cosine, despite cosine x being in the bottom here, that doesn't actually make that big of a difference, if I'm not mistaken. You can still let u be equal to cosine of x, so that du is equal to minus sine x dx, right? This still absorbs the chain rule just fine, because the sine x and the dx are close to each other. The fact that the cosine x is on the bottom means that you might get an ln, or some power rules out of this. You could, but fundamentally, the u substitution still works really nicely because the sine of x is close to the dx. I would imagine that something similar is true for if you had something that looked like secant of x tan x, and you had something like secant to the 7th power down here. U substitution would still be a great candidate because for the exact same reason. The chain rule gets it has a perfect thing reserved for it, right? And I guess the same for tan as well. If you had a secant squared hanging out up here, and you had a tan to some negative power like -8, perfect. Still, you can use u sub. You see that? So don't get fooled if you see some negative powers or things in denominators. It still works out pretty nicely.
Yes.
Okay. How are you feeling? I hope not too overwhelmed.
Yeah, I think I mostly get most of it.
Yeah.
The product. I get the stuff. Sorry about that.
Oh, sorry. I just wanted to mention really quickly, the product identity problems are just for situations that's like sine of, 8x times cosine of 5x. You basically just need to know the formula for these. If you don't know them, you're screwed. All right. If you don't know them, I think it's bad. I think you're going to be in a bad position. But that being said, if you had something like really nicely contrived, like sine of 8x times cosine of, say, 4x, these two are actually really nice because one is the double of the other. So for this particular problem, the easiest way to do it, I would say, is to use the double sine formula, which is sine of 4x, cosine of 4x. So now this becomes a squared, right? And now we get to use the odd sine rule, which is perfect. Yeah, I think that about covers it. Sorry, what were you saying? You were saying, I think, something about the only thing you find difficult, or?
Oh yeah. So I don't even remember what I was saying. I was gonna say, yeah, this stuff seems simple. Like it makes a lot of sense for the stuff that you covered today. Makes a lot of sense. I'll have to look over the other stuff, but hopefully it's fairly more simplistic compared to this.
What's the other stuff? You mean like chapter 8 or 7.8?
I haven't looked over.
Yeah,
because you'd think that they'd like go over the material a bit before, like in class, like not just 2 days before the midterm. But
can I ask, what tutoring structures or what like TA structures do you have for that class? Some people told me that there was like a paid TA program, like you had to pay money to get helped.
So there is so every Monday and Wednesday we have a 50-minute sessions. On Wednesdays we have in-person quizzes.
Okay.
Beyond that, I think there's office hours for free from the what's his name, from the TA and some other people. I know there's like a paid tutoring service. I don't use it, so I don't know.
Right.
I think like I've been fine pretty fine up to like this week, where things have gotten like really stressful.
I see.
For like the past like 2 weeks.
Yeah.
I think a lot of people are probably feeling that too.
Yeah.
Yeah.
I try to, like I said, I'm a hobbyist. I try to help out students. I never actually went through the intro gauntlet myself because I placed out of some of these. But, I think I can try to sympathize. This is my first time doing a review session, and I had to come up with or assemble material notes and figure out how to lecture. So I definitely think it was kind of rough in the middle when I didn't have exactly everything calculated out and was trying to,
I think you did a very good job. Thank you so
Okay.
much. I really appreciate you putting in.
Well, thank you. But, I know that I can sometimes get a little bit choppy if I don't have all the calculations prepared. But in the past, I found a lot of, oh yeah, sure. Let's take a crack at this problem. Just give me a sec. This started about a month and a half back when I was just bored. I'm a software engineer. I wanted to reconnect with math. So I went on Twitch and basically helped anyone that found my channel with their math. One student came in with a bunch of really hard proof-based calculus 1 problems. And all of a sudden, 300 kids came in, all from that class from, I think, York University. And it was kind of crazy. Their professor wasn't helping them out very much. They had never done proofs before. Have you ever heard of epsilon deltas when you took Calc 1?
No.
They're making the nuts and bolts of making a limit rigorous. But it was a crazy situation where I was basically the only resource they had because office hours weren't very good and whatnot. But 400 people started in the class. 300 dropped after the first homework. Of the ones who stayed, quite a few of them told me I was the reason they stayed. And obvious teaching failure aside, because a 75% drop rate is pretty insane, right?
Oh, that's
Crazy.
awful.
Yeah. That aside, I felt like it was something really nice to do. I'm not aware of anybody else who does something like this, but I try to be online, a bit every evening to help students with problems. And when a bunch of students get together with similar problems, similar tough homework problems, I sort of schedule a session and almost like an unofficial TA and walk through them. That's usually more structured because I know the problems to solve. For this one, I kind of had to figure out materials on my own, which, is a bit of a rough trying experience. But I'm hoping that if you think this was helpful, I'd be happy to arrange another one for 7.8. And I think sequences and series, which are probably the hardest part of Calc 2, in my opinion.
Yeah, that would be awesome.
Yeah.
Yeah, that would be really good.
But that's
This is
Wednesday.
really, really helpful.
Yeah, but is there midterm on Wednesday? Is that right?
Yeah, midterms on Wednesday.
Yeah. Anyways, let's take a crack at these problems. That was basically my spiel. I try to help people out. I like math a lot. I perpetually wonder what if I went to grad school instead of industry, but that's another topic. Okay, anyways. This is interesting. E to the 4x plus e to the 4x dx. How would we do this? So is this the problem you want, or do you want to look at the other problem? Which one is it?
Oh yeah, this problem.
Okay.
I looked at this one earlier because it's on our homework, and I think I know how it works.
Yeah, I haven't actually thought about this one myself.
It was like you had to do 2 u substitutions where u equals 4x, and then another u substitution where u where z is equal to e to the u.
Z is equal to e to the u. So then what does this turn into? This turns into z times, what, z to the z? Is that what that is? This is kind of problematic.
I feel like it wasn't that, but it was something. Was it something like that? I'd have to look back, but it was like a weird thing like that where it's do 2 integrals.
Yeah.
From what I remember.
The really hard thing about this is it's really hard when you have something like something raised to itself, because that's neither the power rule nor the exponent rule. That's kind of its own thing. I know how to take. In fact, you can't use the regular integral, you can't use the regular derivative rules either. And I know how to do the derivative for that. I'm not actually sure I've ever thought about how to take the integral of it. but this is literally just e to the u raised to e to the u, right?
Yeah.
So I don't know. Do you think we can get away with just doing integration by parts here? E to the u. Because, okay, if we bump this one up via integration by parts and bump this one down, this would look like e to the u, and then by chain rule, you would get e to the u. Right? That's not helping.
Yeah, it seems more complicated.
This is fascinating. Yeah, I'm not sure. I want to spend a few minutes to take a crack at this. Like, clearly this isn't like any trig integral, is it?
Definitely
I don't
not.
think so.
Definitely
Yeah.
not.
Definitely.
Okay. As you go on in calculus, like, have you ever seen Euler's identity yet? Have you ever seen e to the I pi plus 1 is equal to 0?
Oh yeah, I learned about that in Calc BC, but then I forgot.
Yeah, it's this really elegant identity that you'll see probably before too long when you do power series. But there's actually I would call it a very deep connection between sine, cosine, and e. I won't go into too much of a tangent right now because I'm trying to think about how to do this problem. But yeah, nothing is immediately jumping out to me. This problem is really neat. I like seeing things I've never seen before. E to the 4x plus e to the 4x. So if I was taking a derivative of this, what I would do is I would take the natural log to bump something out. But
I found that the just as like a side note, I found like the homework problems are usually very difficult compared to the it's a really weird homework system too, because we only get a certain number of tries on the problems, and then I think it's like 5, and then if you end up not getting it in 5 tries, you don't get that homework point.
That's pretty
It's
brutal.
really, yeah. So
You got to form a distributed network where you get together with enough friends so you each take one bullet at a time.
it's usually just kind of like looking at like an integral calculator, because it's a really bad homework system in my opinion.
Yeah. Is this
Yeah.
something that came out because of COVID? They're trying to shift things online to minimize contact?
I
I'm-
believe so.
I'm not sure. I'm a
Okay.
first year.
Gotcha. Okay. This might require some genuine thought. What the heck? So, okay, if z is equal to e to the u, this is... So I'm taking the ln sometimes helps with derivatives. I'm going to try taking the ln just to see what I get, if it's more tractable. ln of e to the u, e to the u. So this basically, the ln basically lets you take the exponent out, right? And then it becomes the ln of e, which is just 1. So the ln of the natural log of this integral is really, really nice. Is something nice that we can take advantage of. But can we relate? But we're not interested in the natural log of the integral. We're interested in the straight up, right? We want to get the integral of e to the u plus e to the u. And what I'm saying is I can calculate the natural log of this thing really nicely. Can I relate this to the original expression? I have an derivative trick for multivariable calculus, but I don't think that's appropriate here.
Oh, someone posted how to do it.
Yeah, very interesting.
They said that you can split the problem into EU. Oh my god, this is so confusing to me.
Yeah. I don't know. What do we think? Sorry, I'm running out a quick message.
Yeah, I don't really know how to approach it.
Let's see. Okay, let me try this trick. So I'm wondering if we do integration by parts, if we can relate this integral to the original one.
Maybe.
Yeah, that's a little crazy actually, but I can get you 1 over this thing.
I think I know how this.
Oh yeah, what's
just
the,
looking
do you
at
have an
like
idea?
I'm just looking at the thing the person posted. So
Where are you
after
seeing this, by
get
the way?
just in the study group planning chat.
Okay.
So once they got the e to the u's, they used u substitution where they made z equal to e to the u. I think they split up the e to the u plus e to the u. That sounds really confusing.
Interesting. Let's give that a try.
They split it up, and then they're able to get e to the z, take the integral of that.
I'll give this a crack. E to the u, e to the u, right? And then we're saying we're letting this become z. Works just tested. Very cool. E to the u. So then dz is equal to e to the u du.
Yeah, and then they're able to get e to the z.
So this just turns to e to the z. Wow, very cool. I've never seen that before. And then yeah, this makes total sense. This is just e to the z plus c, and then you just plug it all back in, right? E to the u, and then u was just, sorry, what was u? U was just
It was 4x.
4x. Okay.
I think you might need to do.
Yeah, you're gonna have to do some
1/4.
chain rule, right?
Yeah.
And what, 1/4? Get a 1/4 out of that?
Yeah,
Or
I
something
believe
like
so.
that? Yeah, just be careful of the chain rule, right? But wow, that's cool. That like splits in a weird way that you just wouldn't necessarily expect it to work out. Huh. Very neat.
Yeah, and then just multiply that 3 back in at the end.
Yeah. Yeah, I see that. The other problem that you posted with the problem below it, were you interested in that one as well? Or was it just this weird exponential? Erain?
Oh, sorry, I didn't know that I was muted. Yeah,
Gotcha.
I was yeah, I was interested in that one too.
The ln of x thing? Ah,
Mhm.
well, what this one, I'm going to ignore the constants because, again, they're not all that interesting, right? Okay, I guess we can put 3 in here. And squared, right? What this is screaming to me is that we should use a substitution for ln. Yeah, so if we let this into ln of x, then this turns into u over... Okay, so what is du? Du is 1 over x dx, right? Ah, that's really nice because this x over here is perfect, right? You see what's going on here?
Oh yeah, I see it.
It seems perfectly contrived for us to turn this into some sort of trig integral. Yeah, so this particular x and this dx gets paired together and goes to du, and from here on out, it's a very nice chain rule and very nice trig sub. Make sense?
Oh, wait, yeah, I see it now.
Yeah. So a lot of these problems are all about just clever ways to break things down, and turn them into something you know how to do, right? It's kind of like the textbook and the course notes sort of teach you the basic foundation of stuff, which is like trig and trig sub, and basically they give you all these problems that aren't immediately obviously trig sub, and you just got to like take 1 or 2 steps to turn them into something you know how to do, right? And I mean, this one jumped out to me because the ln and ln of x squared under a square root seemed very, very what do you call it? Contrived or conspicuous, let's call it. But this one over here, I actually really I think is really cool. It's been a long time since I've seen a new, intro level calculus problem that has not been like immediately apparent. It's yeah, just only using U substitutions, you can get something really surprising.
Yeah. Kind of sucks that our homework is so confusing, though. I don't know.
Well, I think it's cool, right? It lets you see, like, some calculus courses are just super computational, and that's what my BC Calc was. But I think it's actually could be really, really good for the way you think to get problems like these here and there to sort of push you, like, to. These are slightly more creative questions than your average calc class, I would say. You could do a billion trig sub problems, and eventually it just becomes muscle memory, right? Problems like these, the e to the u to the e to the u, those are neat. And, if you do take more math, you'll see cooler stuff like that.
Yeah. That's true. Oh, well, yeah. I guess I see what you're getting at. Like, it teaches us to, like, think in, like, a different way instead of just, like, doing muscle memory or doing problems by muscle memory.
Mm-hmm.
Yeah.
How are you two feeling? I think this more or less. My hope here is that maybe when you learn it the first time or through a textbook or through lectures, you basically are given like, this big pile of tools that it's sometimes hard to tell which tool to use over another, right? But I'm hoping that with this session, you kind of have identified which kind of problems go with which tools and a little bit of practice of how to actually do the problems themselves. It's getting some structure.
I feel
right?
pretty good about both these.
That's awesome.
Yeah.
It's good. Well, the hope is that you feel a little bit better than what you came in as, right?
Yeah, you were a lot of help. Thank you.
Okay, that's awesome.
Thank you for holding this
Thank you so
2-hour
much.
session.
Yeah, I appreciate that the two of you stayed through. I think most of our other audience probably had to leave, or I'll try to make things go a little bit smoother if we do this again. But
definitely. I think the videos YouTube will automatically turn the live stream into video.
exactly.
Yeah, definitely post that.
Yeah, it automatically comes up on its own. So in the past, when I did, problem sessions with homework problems, sometimes students would watch those afterwards. And, I don't know if you get the full thing out of it if you are watching it a rerun rather than watching it live, because you don't get to ask questions along the way. I don't know, maybe with review problems, hopefully get more out of it. But, if I could just maybe ask a minute or two of your time, I just wanted to get sort of your feedback on this. This is kind of a new idea, right? As far as I know, I'm the only person who regularly just helps out people who have questions from any class in the country, really, right? Were you too skeptical at all of just getting help from some, random hobbyist? Is that, you know what I mean?
Yeah, I think a lot of people would probably be skeptical because
Right.
it's not usually because a lot of people are expecting some sort of pay, you have to pay for
Right.
something.
Like people, this is typically a paid thing, right? And I expect that I'm trying to get myself into the mind of a student and playing like a, what do I think a student would think situation? And I assume that a student would expect some kind of bait and switch, I don't know, pay money to get access or something like that. But the purpose of this is to keep things relatively egalitarian to where anybody can see it, and anybody can ask questions. Yeah, I guess is there some other way I could have reached out to you that from the start that I think would have made you a little bit less hesitant or just maybe come off better from the start? You know what I mean?
Honestly, I kind of just thought that you were like another student in our class. Just
okay.
So I didn't really think much of it.
Gotcha. Nope, I'm
For me, I'm not exactly sure what would be the best approach, without it seeming weird.
Yeah. Well, Yeah, it's a tough question. With that other calculus, the very first calculus class I discovered, it was basically one person spread it to like 300, 350 other students. And it was like, holy crap, an hour or two of my time every 2 weeks can help so many people. And several of them told me that they would have dropped the class in their major if not for me. Like, that feels like, that, I don't know. I don't want to sound too cheesy, but that sounds kind of incredible to me, right? I kind of want to have that level of impact and scalability when I help out. I don't want to do private tutoring because I don't need the money. And also, it's extremely boring in my experience. One of our other helpers in here in the stream is also a private tutor, so I'm not going to slander the whole business of private tutoring, but I guess it's just not my own thing, right? But it's something to me where I feel like private tutoring or tutoring, just live teaching as a whole, is stuck in the Stone Age. You know what I mean? Like, it's so expensive to get, even an hour of someone's time through traditional means. Like, I assume the rate for one of the tutors associated with the class is probably like $60 an hour, right?
I'm sure they're pretty pricey. I can
pretty steep.
if you'd like, we have like an official discussion board, but it's kind of like moderated, I guess.
Mm-hmm.
I want to say it's like moderated, but like the teacher is on there, whatever. I could post this review session if you'd like on there.
Interesting. So I guess, in regards to that, I never try to do things below board. I don't ever try to help people cheat or give them answers. I try to help people get started with problems when it comes to homework, help them understand. For review sessions, I'm, happy to go in more depth because it's preparing for a test, right? But I'm basically saying, while I never try to help people cheat, I do think sometimes teachers might be a little bit extra hesitant about this idea. Maybe there's a perception of something going on, right? So I guess I just want to be a little bit careful if ever it comes to using an official source.
Yeah,
I basically don't want to get any of you in trouble, right? The professors presumably have no recourse against me, and I'm not going to help anybody cheat. But if the professor gets like some perception of something bad going on, maybe they might make a fuss and make it annoying for everyone, right?
Yeah, definitely.
But if it comes to, if others people directly, I guess I would love it if I could help more people, basically, right?
Yeah, I think word of mouth probably.
Yeah, if and also if you have other classes, I can help with any intro, intermediate, physical science or math class, basically. If you know friends, if you know people who are struggling or want to connect me with other courses, I'm happy to help. I have a decent amount of spare time right now, and basically, if ever I could reach out to a big class and help them. Yeah, one of my friends who is a professional tutor in Germany is saying, from an educator's perspective, I expect much mistrust towards external tutors, which, yeah, right. I understand that. And I can understand a professor's perspective of not wanting to like officially sanction something like this. But, if it's basically like this, if this is an unofficial Discord server, I'm told, right? And if it's just someone helping out with, some problems in preparation for a test, not for an official grade or anything, I'm hoping that, enough people might give it a chance as time goes on, especially if it's a hard course.
Yeah, hopefully. I feel like, I don't know. I just feel like maybe not a lot of people like check the Discord a lot because, I don't know, just because I don't think that a lot of people in this course use Discord regularly, not gonna lie.
I see. Yeah, Discord was relatively new when I was a student. Back when it was unheard of for me to have a Discord for a class. I'm surprised at how busy some classes' Discords are these days. I'm also in touch with, I think, a UC SD, multivariable calculus class that I will also try to, host some review sessions for. But, I think today's session went okay. I'm really happy that the two of you are, really earnest students who ask great questions and, follow along stuff really well. But in the future, I was hoping to also maybe broadcast this to some more people as we go over sequence and series. But that's basically my thoughts.
I have to head out right now.
Yeah, of course.
Just thank you so much. I really appreciate it.
Yeah, take care. And if the two of you want to send me friend requests, I would love to, maybe have some point of contacts in this class. sometimes share. Oh, I think I'm already friended
Yeah,
with Cosmic
I
Snowman.
think you friended me. Yeah.
Yeah, but it's great to have a point of contact to share some either share notes or syllabi or stuff like that.
All right. Well,
but yeah,
thank you
well,
so
take
much.
care and good luck with your
You
class
too.
or whatever it is.
Yeah. Thank you so much.
Yeah.
I think I also need to go too because my AirPods are actually dying. So
Sure. Okay. Well, if you have any other feedback, do let me know. And please let me know if there's some way I could connect with a class. The midterm is on Wednesday, right?
Wait, what happened?
Sorry, is the midterm on Wednesday?
Yeah, the midterm's on Wednesday.
Yeah. Do you feel like most people haven't really started studying yet?
Yeah, I don't think that. Honestly, if it weren't for today, I probably would have started studying maybe like on Monday.
I see. Do you think it would maybe be helpful to do another session on Monday or Tuesday?
Yeah.
And
I think
cover the
that'd be
sequence and
really
series?
helpful.
Okay.
Mhm.
Well, yeah, like I said, I try not to let it bother me too much when people don't show up, but it's inevitably part of starting something new, right? But I would be deeply grateful if you and I guess the other guy left. If you were able to tell maybe some friends or some people about this and maybe vouch for that I can actually help and save them time and frustration.
Yeah, I definitely will.
Yeah, thank you. I appreciate it when students are really earnest and try to help me make a larger impact. But take care and good luck with math and studies.
You too. Thank you.
Okay.
Have a good night.
See ya. Bye-bye. Yeah, Yuli, I definitely understand, like, the idea of lots of mistrust towards an external tutor and whatnot. I get it. But I still think I can do a really good job for a lot of people, just in an unofficial capacity. And yeah. Anyways, it seems to me like the York students are just Yeah, we originally scheduled another York calculus session for today, but I think since no one's really showed up, maybe the session is just canceled. Who knows? Yeah. How are you doing, Yuli? I hope things are going well. They told me that this was the most failed class in all of, I think, UC Irvine. It was the applied math class that was scheduled for today. But, it looks like basically no one's showing up, and it's pretty late anyways, so maybe we just do it some other time. I'm hungry. I haven't eaten all day. But I went through a lot of Calc 2 review. Gosh. Oh, Yuli, I have this explanation that my friend David shared with me for integration by parts that I think you might really like. I was hoping to share it with him earlier, but it's genuinely something that is new to me, and I wish I had learned integration by parts this way. Let me share it with you and see if you think it's as cool as I find it. Oh my god, we wrote so much today. But the idea here is that we essentially schedule. Why did I say the word schedule? We essentially draw this large box, right? The idea here is that if this is u and this is v, and both u is a function of x and v is a function of some parameter x, right? This is going to be u of x naught and u of x1, v of x naught and v of x1, right? So the idea here is that, okay, let's say that u and v are some parametrized curve that go from here to here. The idea behind a visual, you learned it as reverse product rule. Yeah, that's exactly how I learned it too. But this is such a cool visualization that I think it's kind of a shame that I've never heard it until a week ago. But the idea here is that, okay, so if u v evaluated at x naught, x1 is equal to the integral of u dv from x naught to x1 and v du from x naught to x1. Well, this over here is basically u x1 times v x1 minus u of x naught times v of x naught, right? And what this looks like visually is basically the bigger box. You can maybe set this as some like constant, set like this as some limit point or like a fixed point. But basically the idea is u of x1 times v of x1 is basically the larger volume, and it subtracts out the smaller, or I say the larger square, and it subtracts out the smaller square. So it's basically this L-shaped object, right? But then on the right-hand side, it's basically u dv plus v du. And the idea here is that if we essentially look at this curve and imagine this curve as u as a function, if we, on this axis, if we imagine this curve as like v as a function of u, this area, this part of the area, it basically is v du. But wait, it's like if we sort of shift our heads and look on the other side and imagine this part of the curve as u as a function of v, you know, like if you rotate the graph, then this area under the curve is basically v du. You see that? It's like, isn't that crazy? Now, there's a little bit of a scruple here because you need to like account for tiny edge cases, like what if there's a loop in here? Or what if there's like, you know, it doesn't obey the product rule? Or what if it... Oh, hi, Ryan. So York Calculus was originally scheduled for today. But it doesn't seem like there's a ton of people here. You might stick around for 5 minutes to see if people show up after I made that ping. But, you know, if not, maybe we just schedule it for, you know, another night. It's pretty late today. People said that they wanted to do it tonight, but, you know, maybe practice doesn't meet the theory when it's actually 9 p.m. But Yuli, I asked the exact same thing. Isn't this problematic for non-invertible functions? So it's basically like if you fix the horizontal, if you fail the horizontal line test, right? I'm pretty sure that you could always just zoom in and just break it up into enough chunks so that every little chunk is locally invertible. You see what I'm saying? And as for other potential problems like loop-de-loops, right? I think it still works out okay, where I think it gets double counted on one side and then negative counted on the other. And at least visually, at least at a like glance, it seems to work out just okay. But isn't this cool? Like this, I wish that I had seen this because it just makes it click in your head that this is what the heck product rule actually is. And I've been thinking that maybe I should make a couple of these little videos to make a educational footprint on YouTube of cool stuff I found like this. Some of the other students have told me that it would probably help for the long-term growth of the channel if there is live content. Yeah, no, I definitely think that this there might be some holes in here if you try to make it rigorous, but I think the intuition is great. Okay. Hi, folks. Can I ask, when is the applied calculus set due? When is it due? Oh, and by the way, Yuli, I shared the whole. I think it was you that told me that in Germany, what do you call it? That like integration trick where you find the original integral after a couple of integration by parts is called like Phoenix integrals, right? Because the Phoenix bird rises from the ashes. I shared that with the students because I think having a label on a technique tends to make you remember it more. And I'm trying to turn it into a thing. Let's see if we can get enough people in America saying it. Could you share which set you were talking about? I think it is it is not 1300, but the other one. Let's take a look. yeah, maybe we could just go over it really quickly tonight for the students who show. But I was told that, yeah, it's in the York calculus chat. Sorry, it's just in the calculus channel on the Discord. It's like the first one is 2 colored pencils, red and blue. Right? Oh, sorry. That's what applied calculus means. Yeah, it's sorry, which class is which? I'm confused. Maybe this whole thing could have been better scheduled. Maybe we just do it some other day. Sorry. Today I held a review session with Calculus 2, a bunch of kids from UC Irvine, because I'm trying to reach out to that school and that class as well. But I sort of tacked this on afterwards, and I realized it's kind of late. 1300 is a theory-based one. Gotcha. I actually haven't really taken a look at that yet. Actually, I don't even know if anybody's shared it with me. Does someone want to share it with me, or? Remind me, 1300 is the proof-based class where there was 400 students at first and 300 dropped, right? Yeah, we're probably not going to be able to have time to go over it today. I think it would help to see the questions if someone either wanted to put them in one of the Discord chats or DM'd it to me. Either way is fine. Wow. I've noticed that I have really poor control of my voice when I'm wearing headphones. I think I really need the feedback of how my voice actually sounds to control my volume. Wearing headphones when going on Discord calls, my voice just tends to go totally weird. Some very few of your old professors were kind of proud of the low passing rate. That's so brutal. I had a stat student from, I think, UC, University of Colorado Boulder, who said that some professors in his business management part said out loud that the stats class was a weed out and was, there so that not too many of them got into the major, which is hilarious because we all know that's how most universities work. But usually you'd think that people have the feel the need to not say the quiet part out loud, right? I feel like you're not so. It's not so nice to actually say that. Okay, thank you, Gaga. Okay, so I'm looking at these problems. Prove that the equation. Okay, so it's an 8th order polynomial, has no more than 2 solutions. Interesting. So my guess is that what's going to happen here is that it just doesn't have. Okay, so an 8th order polynomial could have up to 8 solutions, right? But the idea is that, if it just doesn't have enough curves, right? If it doesn't have enough curves, an 8th order polynomial could still look very simple, just like this, right? And that only has 1 solution. It could look a lot more complicated, but it's basically saying how much complexity does this equation have, right? How many times does it turn around? And I think the idea here is, since we're talking about the second derivative, we probably want to show that the second derivative, I don't know. I don't know if off the top of my head, but we probably want to show that it's, positive all the time, or maybe negative all the time, so that it only has like 1 critical point and only turns around once. Because every time, in order to have more solutions, the function needs to turn around more times, right? And you would pick up more critical points if that's the case, and you would see that the second derivative would also be changing. So I think that's the idea. I don't know how to do it yet, but that should be the intuition. So if g is defined by the same function, and a is less than b, then the graphs of g never crosses the line segments connecting the points. Interesting. A is less than g. A is less than b. Yeah. People probably on break. Makes sense. Makes sense. I hope you all are doing well. I had some nice conversations with some students who told me I saved them. Like, I had some nice conversations from the students in the other applied calculus class who told me that, you know, more than anything, it was that I saved them time and frustration. And usually when they start a problem, they're just staring at it blankly for hours. And they say that the biggest help is that I help cut down on some of the unproductive time and make sure that they're focused on productive stuff. And I think that's a decent way to think about it. But, okay, so if g of t is equal to 8t to the 8 plus 3t squared never crosses the line segment, crossing the points. Okay, so what's this turn into? A g of A and B g of B. So I'm assuming that if the function looks kind of like this, it's probably going to be convex up. Show that the derivative only has one root, and it follows that the function must have two roots. Yeah, I mean, I think that's a pretty reasonable line of thought. I haven't completely thought it through myself, but function doesn't even have a root because t to the 8 increases too fast. Oh, I see what you're saying. T to the 8 increases too fast. Sure, okay. But I guess they're asking you to show that there's no more than two, even hypothetically, just because it looks kind of like a parabola, right? Because it only, you know, has one critical point and, you know, is convex upwards. The idea is that a parabola can only, something that looks a lot like a parabola can only have two roots, just the way it's shaped. And I assume for the next one, it looks like it's, you know, a property of convexity. Think about what convexity means. It sounds like it's basically saying if this is A and this is B, show that this line segment lies above this line. Yeah, it basically is the definition of convex, except for it needs to, I think you need to omit the endpoints, basically. Okay. And then it's reading through something and trying to find an error. Okay, I don't feel like doing that right now. I'm too hungry and tired. I haven't eaten breakfast yet, and it's 8 p.m. All right, folks. Hey, thank you all for joining us today. But I think I'm going to have to call it there. I'm just too starving. But I hope you all have a great evening, and take care. Take good care. Imagine a sign error. Yeah, I know. I feel like in the future it should be, problems would be better if they have significant mistakes to them rather than sign errors. It's brutal.